Here we go to the julialang.org. We go to the download tab and select the generic Linux on x86 and download the 64-bit version of it. There are other versions of Julia that we can install, for example, the long-term support, which is at the moment version 1.6.7. You can download the 64-bit version of it. There are also other supported versions and the release scheme for the Julia that you can look up on their website. After downloading Julia and unpacking it, we go to the bin folder, open the terminal, and we do the pwd and copy the path. Here I've got a command for the terminal that you can use to make a symlink between the Julia in the bin folder that you have unpacked and symlink it to the user local bin Julia. Now I paste the symlink command into the terminal. Here I will type my password, and after that I will test the Julia language. I'll type 2 to the power of 10. As you can see, it works. In this tutorial, we are going to install Julia on Windows. First, we will go to the julialang.org, go to the download tab, and the current stable release is version 1.9.3. For Windows, there are two installers. One of them is the regular installer, and the other one is the portable version. I download the portable version. As you can see, I have already downloaded the portable version. So I extract it into the C drive. After it has been extracted, I'll go to the Julia bin folder. As you can see, there is a binary version of the Julia. I double click to test it. It works. I copy the path of the bin folder. I go to the system environments on Windows 10 and go to the environment variables, search for path, double click, add the copied path to this list, to the list of environment variables. After that, I click OK and apply. I go to the command prompt and test the Julia. Or if I have the command prompt already open, I close it and reopen it. So as you can see, it's the version 1.9.3. I test it with 2 to the power of 10. It works. In this tutorial, I'm going to show you how to use the REPL in Julia. REPL stands for Read, Evaluate, Print, Loop. As you can see, you can type question mark for help and left square bracket question mark for package help. So if I type question mark, I go into the help mode of the Julia. For example, if I type array, I get the help information for the array. As you can see, it provides some information about how to use the array in Julia. For instance, the array method and the other usages for it. For instance, if I type status, I can get information about the contents of the current environment that I'm using in Julia. For example, over here you can see that I have the JSON package installed. If I use the rm command, as an example, rm.json, I can remove the package from the Julia environment that I'm using currently. I can use the add JSON to add a package to my current Julia environment. I can use the question mark to see the commands that I can use while I am in the package mode in the REPL. You can switch to the package mode by using the left square bracket while you are in the Julia REPL, and you can use the backspace to get out of the package mode in the Julia REPL. Package mode provides information about the commands that you can use in this mode in Julia REPL. Update or up command can be used to update the package in Julia. For example, update JSON or up JSON updates the package. I think that's enough to know to start programming in Julia. In this tutorial, we installed Visual Studio Code for using with Julia. I have already downloaded the Microsoft Visual Studio Code installer. I click Next and install it in C drive. Remember to add Open with Code to the context menu so you can open a directory with Visual Studio Code. After installing the Visual Studio Code, you'll see the welcome page. So you can skip it, or you can uncheck the show welcome page at the startup, so it never pops up again. After that, you go to the extension section in the Visual Studio Code and search for Julia extension and install the Julia on VSCode. This extension gives some utilities that you can use and integrate Julia with the VSCode environment. I open up a folder, call it Julia project. Then I double click and open the VSCode inside this directory. I check the trusted authors of the files in this folder. After that, I will create a new .jl file. Now, if you look at the sidebar, near the sidebar, there's a Julia icon. If you click on it, you will see that the extension is working and has integrated with the VS Code environment. So I'll type something in the example 1.jl, for example, println numeris.com. And as you can see, if I run the Julia execute active file in the REPL, you see it prints the numeris.com, and I can test the opened up REPL environment in the terminal below the VS Code. As you can see, it works. In this tutorial, I'm going to talk to you about the Julia variables and some concepts like constants in Julia, comments in Julia, and finding the types of the variables in Julia. To define a comment in Julia, we use a hash sign and we write our comment. We usually use comments while we are actually explaining our code snippet to someone else. For example, someone else will come and read your code, and by reading the comments that you have provided, he can understand that line, that snippet of code. For using a multi-line comment, we use hash equal sign and write our multi-line comment and end it with equal hash sign. If I don't use the equal hash sign, the whole lines that all lines that come after the hash equal sign will be considered as a comment, as you can see. So we have to end it with equal hash sign. To define a variable x and assigning a value 12 to it, we define it like this: x is equal to 12. And to get the type of the variable x, we use the function typeof, which gives us the concrete type of x. And there are some examples provided over here in the VS Code extension of Julia. For example, if I run this line, you'll see that I get the int64. I've actually run this line by using the control enter, or you can use shift enter to run the line and go to the next line. Over here, x is equal to, we can assign another value actually to x by manipulating the variable that we had defined before. X is equal to x plus 10, as you can see. We can define several variables in one line. X is equal to 12, y is equal to 15, and z is equal to 18. We have actually assigned several values, 12, 15, 18, in one line to variables x, y, z respectively. And y is equal to x power 4 plus 2x is another way of manipulating variables and assigning them to another variable. We can change the data type of the x, and actually we had assigned value 12 to x over here. Now we are assigning a string to x. So we are dynamically changing the data type of the variable. Over here we have assigned the numerous.com to x. And if we run this line and go and check out the type of the variable x, as you can see, it's a string. But before that, it was int64 because we had assigned the value 12 to the variable x. Over here, you can see I've assigned the value 3.14 to the variable w, and we can check the type of it. As you can see, it said float 64. A variable name cannot start with a number, but you can use uppercase, lowercase, and underscore. For example, over here, we have used underscore xyz, and it's considered a variable. We can print the xyz's value or the data that it holds like this in the REPL. And you can see 432. We also can use Unicode characters for variable or function names in Julia. We can actually define the gamma by using /gamma and writing tab. For example, I can type gamma and use tab and assign a different value. Over here, gamma is equal to 45, and over here, gamma is equal to 12. You can write alpha by using /alpha and then hitting tab on keyboard. So over here, I had already defined the alpha equal to 15. I can get its value in the Julia REPL because I am not using the semicolon. It prints the last result and prints 15 in the REPL. You can write superscripts or subscripts by using Unicode characters in Julia, and they are considered as a variable name. But I don't recommend them for complex programs because it makes your program confusing while you're actually calling the names of these variables, because they are hard to handle when they become a lot or when they are scattered in different parts of your code. So over here, I can use beta. I can type beta tab and /_0 and tab again. And as you can see, it types beta subscript 0. And gamma superscript 1 is written as gamma. You type gamma, press tab, and use /, type this, and you can want to actually gamma to the power of 1. Or gamma, over here, it's not gamma to the power of 1, actually, it's gamma superscript 1. And we can assign a different value to it. You can see that it prints the value 11 in the Julia REPL. There are some keywords in Julia that are reserved and you cannot use them as a variable name. For example, over here I've used a multi-line comment and listed them over here. You can check this out in the documentation of the Julia. Bare module, begin, break, catch, const, continue, and the list goes on. For example, I cannot define begin as a variable. It throws an error, and it has thrown an error, and we cannot use the reserved keywords as a variable name. The same is holding for if. As you can see, it throws an error. So I comment this line, and there are some predefined constants in Julia. For example, pi. We can type pi in the Julia by typing actually /pi and hitting tab. And its value is defined as the value of the constant pi. Pi and hitting tab gives the value of pi. And there are other predefined constants like the Euler constant. You can type /Euler, hitting tab, and we get its value. See, there are some naming style conventions in Julia that you can use for your variable names, function names. We can break the several word variable names by using underline between them, or underscore between them. And for example, over here we can define the variable first name like this and assigning the value numerous to it, or we can use lowercase for the first part and start the second words character with a uppercase letter, and the rest of it be the lowercase. And there are several other naming style conventions for defining variables in Julia. We can also assign values to multiple variables in one line. For example, I have defined P, Q, R and assigned 8, 9, 10 to them respectively. As you can see, the P holds the value 8, Q value 9, and R value 10. We can swap the values of the variables by using this one-liner code. P comma Q is equal to Q comma P. But in other languages, we have to define an intermediate variable which holds value of the one of the variables while swapping the values of these two variables. For example, here we can easily use this one-liner to swap the values. You can see P holds the value 9, Q holds the value 8. But before that, P hold the value 8 and Q hold the value 9. Till now, we didn't define the variable types, and Julia would automatically infer the types of the variables. We can define variable types as easily as specifying them like this, as I have commented over here, specifying them like this. We can use the variable name and double colon and the variable type. For instance, we can define the variable u and use double colon and specify its type as int64. This has common use, and specifying the types of variables helps us actually in defining functions that we haven't yet talked about, and using features like multiple dispatch, catching errors, and code readability for others that actually read our code, so they can know beforehand what the type of the variable that they are dealing with is. For example, over here, I haven't actually talked about the functions, but over here I have defined the function sum2numbers. It's the function name, and this is a reserved keyword in Julia to define a function. And it takes two input arguments, and x and y. I have defined the x to be the type of float64 and y to be the type of float64, and it returns the sum of these two arguments that are passed to the function. So if I define this function, sum2numbers, and I call them with two integers as inputs to the function, as you can see, it throws an error and calls us that no method matching sum2numbers in 64, because we have already specified the data type of x and data type of y, and 12 is an integer, and another argument, the second argument 12 is also an integer. But if I comment this line and run this code, since we are passing the floating point number 12, the error goes away, and it actually prints the sum of these two values. If I change this to, for example, 13, 25, as you can see. Another question is, how can we validate if an expression is of a particular type? For example, we can use expression, double colon, and expression type. This way we can catch errors. For example, over here I have summed the 7 plus 8 and 7 plus 8 times 2. I want to see whether the result of this expression is of the type int64. As you can see, the result is printed in the REPL, and the Julia REPL actually hasn't thrown any error for the result of this line. But what about this line? Over here, we have actually multiplied the sum of 7 and 8 by floating point number. So it's the whole expression is converted to the floating point number, and it's not of type int64. This must throw an error. As you can see, it has thrown an error expected int64, but got a value of type float64 because of this multiplication by floating point number 2. If I comment this line and go to the next line, you can see we get the expected type float64. Over here, it's float64 also. To declare a constant, we can use the const keyword in Julia, but you have to be aware that using the const keyword and the name of the constant, over here, for example, we have assigned the value numerous to the constant myHandle. But if I change the value to another data type, if I change the value of this constant to another data type, Julia REPL throws an error and says invalid definition of constant myHandle, because we have changed the type of this constant. We have first defined it as a string and then assigned a value of a different data type to this constant. So the Julia REPL throws an error. But if I assign a value to this constant of the same data type that I had already defined this constant with, that is a string over here, the Julia compiler actually does not throw an error but a warning. And in this warning, it says that redefinition of the constant myHandle, this may fail and cause incorrect answers or produce other errors. So the constant is actually a mutable thing in Julia. You can change its value, but you cannot change its data type. In this tutorial, I'm going to talk about the types in Julia. I start with two claims. The first one is Python is a dynamically typed language. And the other claim is Julia is an optionally typed language. Julia can also be considered a dynamically typed language. But what does that mean? Julia is actually a dynamically typed language. Though if you specify a type like variable, double colon type, you can think of that variable as being statically typed. And this will improve performance in cases where the compiler couldn't automatically infer the type. Actually, what is the definition of the type? Data elements come in different shapes and sizes, which are called types. Consider the following numeric values. For example, a floating point number, a rational number, an integer. These three different types of numbers, and in general, in different data types, can take different amounts of memory in the computer. The type of function gets the concrete type of x, and x is passed to the type of function. For example, type of 0.5 and type of the rational division of 1 divided by 2, and type of the integer 1. For example, the type of 0.5 is float64. The type of 1 rationally divided by 2 is rational int64, and the type of integer 1 is int64. Basically, it's easy for us humans to add these numbers without much thought, but a computer won't be able to use a simple addition routine to add all three values. For example, the integer and the floating point number and the rational number, because these are different types. Code for adding rational numbers has to consider numerators and denominators, whereas code for adding integers won't. The computer will probably have to convert two of these values to be the same type as third. Typically, the integer and the rational will first be converted to floating point, then the three floating point numbers will be added together. Actually, this business of converting types obviously takes time. So to write really fast code, you want to make sure that you don't make the computer waste time by continually converting values from one type to another. When Julia compiles your source code, which happens every time you evaluate a function for the first time, any type indications you've provided allow the compiler to produce more efficient executable code. Another issue with converting types is that in some cases you will be losing precision. Converting a rational number to a floating point number is likely to lose some precision. The official word from the designers of Julia is that types are optional. In other words, if you don't want to worry about types, and if you don't mind your code running slower than it might, then you can ignore them. But you'll encounter them in error messages, the documentation, so you will eventually have to tackle them. A compromise is to write your top-level code without worrying about types. But when you want to speed up your code, find out the bottlenecks where your program spends the most time, and clean up the types, in that area, you'll have to know about the types. The typing system, there is actually a lot to know about the Julia's type system, so the official documentation is a place to go, but here's a brief overview. Here's the Julia's type hierarchy for the number types. In Julia, types are organized in a hierarchy with a tree structure. At the tree's root, we have a special type called any, and all other types are connected to it directly or indirectly. Informally, we can say that the type any has children. Its children are called any subtypes, and a child's supertype is any. As you can see, we have a good example of Julia's type hierarchy as you're looking at the number types in Julia. The type number is a direct child of any. To see what number's supertype is, we can use the supertype function. For example, we can type supertype number and see the value of it in the Julia's REPL. But we could also try to find numbers subtypes. Numbers children, therefore any's grandchildren. To do this, we can use the function subtypes. We type subtypes number and we'll get the numbers children. And we can observe that we have two subtypes of number, complex and real. For mathematicians, real and complex numbers are both indeed numbers. As a general rule, Julia's type hierarchy reflects the real world's hierarchy. In this tutorial, I'm going to talk to you about Julia programming language types. We have already talked about how to set up Julia for using it with VSCode. Over here, I define a function called +1. Then I remind you the definition of types in Julia and define the concrete types and abstract types. +1 function gets a number and returns the same number +1. I will show you how to define functions in Julia in future videos. Data elements come in different shapes and sizes, which are called types. Consider the following numeric values: a floating point number, a rational number, an integer. Each object in Julia, informally this means everything you can put into a variable in Julia, has a type, but not all types can have a respective object, that is, instances of that type. The only ones that can have instances are called concrete types. Concrete types cannot have any subtypes. The types that can have subtypes, for example, any number, are called abstract types. Therefore, we cannot have an object of type number since it's an abstract type. In other words, only the leaves of the type tree are concrete types and can be instantiated. We can divide concrete types into two categories: primitive or basic and complex or composite. Primitive types are the building blocks usually hard-coded into Julia's heart, whereas composite types group many other types to represent higher data structures. For example, in this diagram which shows Julia's type hierarchy for the number types, we can see the subtypes of the number. For example, real and complex are abstract types, rational and integer are abstract types. Fixed point, abstract, irrational, abstract float are abstract types. Over here, the leaves of the tree, for example, uint 8, uint 64, uint 32, uint 16, uint 128 are concrete types. You'll probably see the following primitive types: the basic integer and float types, signed and unsigned; more advanced numeric types, big float, big int; Boolean and character types, bool and char; and text string types, for example, like a string. A simple example of a composite type is rational, used to represent fractions. It's composed of two pieces, a numerator, a denominator, which both are of type int. In this example, the function expects a variable n. The type of n must be subtype of number, directly or indirectly, as indicated with the double colon syntax. What does this mean? No matter if n's type is int, integer number, or float 64, floating point number, the function +1 will work correctly. Furthermore, +1 will not work with any types that are not subtypes of number. For example, text, strings, arrays. Now we pass some arguments to the +1 function and see its functionality. As you see, if I pass the integer 1, I get the 2. But if I pass a string example, I get a method error, no method matching +1, because we have already specified the type of the variable which is passed to the function as the type of number. As you can see, since the floating point number is a subtype of number, we can pass floating point also to the +1 function, as well as a rational number. Julia provides two functions for navigating the type hierarchy: subtypes and supertypes. For example, if I type subtypes integer, I get the subtypes of the integer type. And if I type supertype float64, I get the supertype of float64 type, which is an abstract type. The size of function tells you how many bytes an item of particular type occupies. For example, size of big float, which is 32, and size of char, which is 4. If you want to know how a big number you can fit into a particular type, these two functions are useful. Type max int 64, for example, returns the maximum value that you can put into int 64, and type min int 32 returns the minimum number that you can put into int 32 type. There are many types in the Julia-based system. You can investigate the type hierarchy with the following function. I define a showType3 function, which I'll explain later in the future videos, probably. This function actually lists the subtypes of a particular type. As I've already executed the showType3 definition in the REPL, I will call the function and pass the number type to print the subtypes of number in Julia. You can see that it prints the subtypes of number as specified and illustrated in the slides previously. We have already seen that Julia does its best to work out the types of things you put into your code. If you specify them, for example, over here, collect colon 10, which is a function which returns a vector of numbers between 1 and 10. As you can see, its type is int64. And if we pass the one floating point number colon 10, the Julia automatically infer the type of the vector which is returned. As you can see, it's printed in the REPL as float64. In Julia, it's very easy for the programmer to create types benefiting from the same performance and language-wise integration that native types, those made by Julia's creators, have. For example, abstract type. For defining an abstract type, suppose we want to create an abstract type. To do this, we use Julia's keyword abstract followed by the name of the type you want to create. Over here, I type abstract type and specify my type name. For example, my abstract type, and end it with the end keyword. By default, the type you create is a direct subtype of any. If I type super type and pass the already defined type, my abstract type, to it, it returns any. You can change this using the less than colon operator if you want your new abstract type to be a subtype of number. For example, you can declare something like abstract type less than colon number and end it with the keyword end. But the problem is, as you can see, the REPL throws an error, invalid redefinition of constant my abstract type. We have to notice that in the same Julia session, without exiting the REPL or ending the script, it's impossible to redefine a type. That's why we have to create a another type, another name for our type. So over here, I modified it to my abstract type 2 and executed it. In Julia, we can also create new composite types. To do this, we use the struct or mutable struct keyword, which have the same syntax as declaring the supertype. The new type can contain multiple fields where the object stores values. As an example, let's define a concrete type that is subtype of my abstract type. We just created a composite struct type called myType, a subtype of my abstract type, with two fields, foo that can be of any type and bar that is of type int. How do we create an object of myType? By default, Julia automatically creates a constructor, a function that returns an object of that type. The function has the same name of the type, and each argument of the function corresponds to each field. In this example, we can create a new object by typing, for example, x is equal to myType and pass a string as the first argument, over here hello, and an integer as the second argument. And as you can see in the REPL, myType hello and 10 is printed. This creates a myType object, assigning hello to the foo field and 10 to the bar field. We can access x's fields by using the dot notation, and the bars fields by the dot notation also. We can also modify the value of the foo field and passing a floating point number to it. And in addition, modifying the bar field's value to another integer, because we have already specified the type of bar field to be integer. For example, if I modify the value of the bar field and pass it a string like hello to it, you will see the REPL throws an error, method error, cannot convert an object of string to an object of type int64. I think that wraps up the basic fundamentals for understanding the types in Julia, and we have already covered how to define abstract types and how to define structs. And in the upcoming videos, we will dive into more details about types and talk about the concepts like type instability and other concepts alike. In this tutorial, I'm going to talk about Julia's if-else loop. I will explain these concepts in detail, and before we dive into coding, I have to clarify some basic concepts. There are different ways to control the flow of a program. Typically, each line of a Julia program is evaluated in turn. There are various ways to control and modify the flow of evaluation. These correspond with constructs using other languages: ternary and compound expressions, Boolean switching expressions, if, else, else, and conditional evaluation, for and iterative evaluation, while and try and catch error. Often you'll want to do job A or call function A if some condition is true, or job B, function B if it isn't. The quickest way to write this is use the ternary operator, that is question mark and colon. In this example, I'll define a variable and assign the value 1 to it, and use the ternary expressions to decide whether to print yes or no. For example, if x is greater than 3, it prints yes, and if it isn't, it prints no. Here is another example. I'll assign the value 0.3 and use the ternary expression to calculate sine or cosine of the x. For example, over here, x is less than half, so we'll calculate the sine x. Boolean switching expressions. Boolean operators let you evaluate an expression if a condition is true. You can combine the condition and expression using double ampersand or double pipe. Double ampersand means and double pipe means or. Since Julia evaluates expressions one by one, you can easily arrange for an expression to be evaluated only if a previous condition is true or false. The following example uses a Julia function that returns true or false depending on whether the number is odd. We use is odd and pass the value into it. With double ampersand,
both parts have to be true, so we can write something like this. If the first condition, number is odd, is true, the second expression is evaluated. If the first condition is not true, the expression is not evaluated and just the condition is returned. With the double pop operator, on the other hand, we have something like this. If the first condition is true, there is no need to evaluate the second expression since we already have the one truth value we need for OR, and it returns the value true. If the first condition is false, the second expression is evaluated, because that one might turn out to be true. This type of evaluation is also called short circuit evaluation. But what about if and else? For a more general and traditional approach to conditional execution, you can use if, else if, and else. If you're used to other languages, don't worry about white space, braces, indentation, brackets, and semicolons, or anything like that. But remember to finish the conditional construction with the AND keyword. For example, over here I assign the value Julia to the variable name and write the conditional expressions. I'll use an if, else if, else block. Also note that the else if and else parts are optional too. For example, I can assign the value Julia to the variable name and check if the name is equal to Julia and print something like I like Julia. Just do not forget to use the AND keyword to finish the block. You might ask the question about the switch and case statements which are available in other languages. Well, you don't have to learn the syntax for those because they do not exist. Also, there is an if-else function too. It looks like this in action. If-else is an ordinary function which evaluates all the arguments and returns the second or third depending on the value of the first. With the conditional if or question mark double colon, as we have seen in the ternary expressions, only the expressions in the chosen route are evaluated. Alternatively, it's possible to write things like as you can see, we have assigned the value returned by a conditional block to a variable. For loops and iteration. Working through a list or a set of values, or from a start value to a finish value, are all examples of iteration. And the for and construction can let you iterate through a number of different types of objects, including ranges, arrays, sets, dictionaries, and strings. Here's a standard syntax for a simple iteration through a range of values. The variable I takes the value of each element in the array, which is built from a range object in turn. Here is stepping from 0 to 100 in steps of 10. For example, I'll give you an example of an array, a string, a tuple, a dictionary, a set, and iterate through them with the for loop. We haven't yet met sets and dictionaries, but iterating through them is exactly the same. You can iterate through a 2D array, stepping down through column 1 from top to bottom, then through column 2, and so on. You can use the equal sign instead of in keyword for the for loop in the following example. Loop variables and scope. The variable that steps through each item, the loop variable, exists only inside the loop and disappears as soon as the loop finishes. For example, in the following for loop, the I is not defined outside the loop. If you want to remember the value of the loop variable outside the loop, for example, if you had to exit the loop and needed to know the value you'd reached, use the global keyword to define a variable that outlasts the loop. For example, in the following for loop, I'll define a global variable called howFar. Here, howFar didn't exist before the loop, but it survived to tell its story when the looping was over. If howFar existed before the loop started, you can change its value only if you use the global in the loop. Working in the REPL is slightly different from how you write code inside functions. In a function, you would write something like this. Variables declared inside a loop. In a similar way, if you declare a new variable inside a loop, it won't exist once the loop finishes. In this example, k is created inside, so it does not exist after the loop has finished. Variables created inside one iteration of a loop are forgotten at the end of each iteration. In this loop, for example, z is created afresh each time. If you want a new variable to persist from iteration to iteration, it has to be global. For example, over here I define the variable counter as a global variable. To see this in more detail, consider the following code. Perhaps you expected only the first loop to produce the z is not defined error. In fact, even if z is created in the body of the loop, it isn't defined at the start of the next iteration. Again, we use the global keyword to force z to be available outside the loop once it has been created. Although if you are working in global scope, z is now available everywhere with the value 10. This behavior is because we are working in the REPL. It's generally better practice to put your code inside functions, where you don't need to mark variables inherited from outside the loop as global. Now we go to the section that is fine-tuning the loop with continue keyword. Sometimes on a particular iteration you want to skip to the next value. You can use the continue to skip the rest of the code inside the loop and start the loop again with the next value. In the following example, I'll show this. Now we go to the section about while loops. To repeat some expressions while a condition is true, use the while end construction. For example, I define a variable, assign the value 0 to the variable x, and while x is less than 4, I will print the value of the variable x and define the global variable x inside the loop and increase its value by 1. Now we are going to talk about functions in Julia. But what is a function? A function is a collected group of instructions that can return one or more values, possibly based on the input arguments. If the arguments contain mutable values like arrays, the array can be modified inside the function. By convention, an exclamation mark at the end of a function's name indicates that the function may modify its arguments. There are various syntaxes for defining functions. When the function contains a single expression, when the function contains multiple expressions, when the function does not need a name. Single expression functions. To define a simple function, all you need to do is provide the function name and any arguments in parentheses on the left and an expression on the right of an equals sign. These are just like mathematical functions. For example, I defined f equal to x squared function and I passed the value 2 and get the value 4. Now I defined a multivariable function gxy which calculates the square root of x squared plus y squared. Then I pass the value 3 and 4 to it and calculate the value. Functions with multiple expressions. The syntax for defining a function with more than one expression is like function, function name, and then you pass the arguments, and in the function's body there are several expressions, and it ends with the end keyword. Here's a typical function that calls two other functions and then ends. Here I define the function breakfast and call two other functions make toast and brew coffee. Whatever the value returned by the final expression, here I mean the brew coffee function, that value is also returned by the breakfast function. You can use the return keyword to indicate a specific value to be returned. For instance, I defined a function can pay the bills and pass the bank balance argument to it. If bank balance is less than 0, I return false, else I return true. Some consider it good style to always use a return statement, even if it's not strictly necessary. Later we'll see how to make sure that the function does not go adrift if you call it with the wrong type of argument. Returning more than one value from a function. To return more than one value from a function, use a tuple. For instance, I defined a function double 4 and return a tuple of 2 4s, optional arguments and variable number of arguments. You can define functions with optional arguments so that the function can use sensible defaults if specific values are not supplied. You provide the default symbol and value in the argument list. For example, here I define a function called xy pose and pass the arguments x, y, and z and set the z to the default value 0. Then I print the xyz arguments passed to the function xyz pose. And when you call this function, you don't provide a third value. The variable z defaults to 0 and uses the value inside the function. I tested with two different arguments. The first one I passed the value 1, 2 to it, and the other one I passed the value 1 to 3 to it, and then print the arguments. Keyword and positional arguments. When you write a function with a long list of arguments like fpqrstu, sooner or later you'll forget the order in which you have to supply the arguments. For example, it can be f and pass the string 42 and minus 3.143 and etc., or the other one. You can avoid this problem by using keywords to label arguments. Use a semicolon after the function's unlabeled arguments and follow it with one or more keyword equal to value pairs. For example, over here I define a function f and pass the p and q arguments, and after the semicolon I default the value of the r argument to 4 and s argument to the string hello. Then I print the p and q and return the r and s value. Then call this function expects two arguments and also accepts a number and a string labeled r and s. If you don't supply the keyword arguments, their default values are used. However, if you supply keyword argument, it can be anywhere in the argument list, not just at the end or in the matching place. When defining a function with keyword arguments, remember to insert a semicolon before the keyword value pairs. Here's another example from the Julia manual. The RTOL keyword can appear anywhere in the list of arguments, or it can be omitted. A function definition can combine all the different kinds of arguments. Here's one with normal, optional, and keyword arguments. Functions with variable number of arguments. Functions can be defined so that they can accept any number of arguments. For example, I defined a function fvar and passed the args 3 dots to it. The 3 dots indicate the famous splat. Here it means any, including none. You can call this function with any number of arguments. For example, I can call the fvar function without any arguments or 0 number of arguments. Or I can pass 1 argument to it, 2 arguments to it, and 3 arguments to it, and so on. Here's another example. Suppose you define a function that accepts two arguments. You can call this test function in the usual way. If you have two numbers but in a tuple, then how can you supply a single tuple of numbers to this two-argument function? Again, the answer is to use the ellipsis or splat. That is, I pass the tuple to the test function and I follow the tuple with three dots. The use of ellipsis or splat is also referred to as splicing the arguments. You can pass a list to the test function also and use the splat operator. You can also combine the map function with the splat operator and a list. For example, pass the 4 and 6 arguments to the test function, local variables, and changing the values of arguments. Any variable you define inside a function will be forgotten when the function finishes. For example, I define a function test and pass the arguments a, b, c to it, and then calculate the subtotal, that is the summation of the a and b and c, and return the value. However, if I call the function test and after that call the variable subtotal, I get the undefined variable error, subtotal not defined. If you want to keep values around across function calls, then you can think about using global variables. A function cannot modify an existing variable passed to it as an argument, but it can change the contents of a container passed to it. For example, here's a function that changes its argument to 5. Although the x inside the function is changed, the x outside the function is not. Variable names in functions are local to the function. But the function can modify the contents of a container, such as an array. This function uses the opening bracket colon closing bracket syntax to access the contents of the container x, rather than change the value of the variable x. Here I define the function filled with 5 and use the aforementioned syntax to access the contents of the x container. I create an array x and pass it to the fill with 5 function. The function fill with 5 modifies the content of the container x. You can change elements of the array, but you can't change the variable so that it points to a different array. In other words, your function is not allowed to change the binding of the argument. Anonymous functions. Sometimes you don't want to worry about thinking up a cool name for a function. Anonymous functions with no name, can be used in a number of places in Julia, such as with map and in list comprehensions. The syntax uses dash greater than like this: x dash greater x squared plus 2x minus 1, which defines a nameless function that takes an argument, calls it x, and returns the x squared plus 2x minus 1. For example, the first argument of the map function is a function, and you can define a one-off function that exists just for one particular map operation. For example, I can pass the anonymous function as the first argument to the map function and pass a list of arguments as the second argument to the map function. After the map finishes, both the function and the argument x have disappeared. So if I call the x variable, I'll get the message that x is not defined. If you want an anonymous function that accepts more than one argument, provide the arguments as a tuple. For example, I can define a function which is anonymous and pass it as the first argument to the map function, and pass as the second, third, and fourth arguments of the map function. I can pass 3 lists of numbers. Note that the results are 12, 15, 18 rather than 6, 15, and 24. The anonymous function takes the first value of each of the 3 arrays and adds them. followed by the second, then the third. In addition, anonymous functions can have zero number of arguments if you use an empty tuple. For example, I can define an anonymous function and assign it to the variable named random. Map. If you already have a function and array, you can call the function for each element of the array by using the map function. This calls the function on each element in turn, collects the results, and returns them in an array. This process is called mapping. For example, I define a vector from 1 to 10 called a and map the elements of a to the sinus function. Map function returns a new array, but if you call map exclamation mark, opening and closing parentheses, you modify the contents of the original array. Often you don't have to use map to apply a function like sign to every member of an array, because many functions automatically operate element-wise. The timings of the two different versions are similar. Sign dot opening and closing parentheses function has the edge perhaps. Comparing the performances, depending on the number of elements of the argument that is passed to these functions. We can compare the performance of the map function and sign dot by using the add time and comparing the results. Map function collects the results of each application in an array and returns the array. Sometimes you might want the mapping action, but you don't want the results returned as an array. For this job, use for each. For example, I use for each print line and pass an array, and the result will be printed. But if you check the ans or answer variable, you see that it is equal to nothing. And this shows that the results are not returned as an array. Map with multiple arrays. You can use map function with more than one array. The function is applied to the first element of each of the arrays, then to the second, and so on. The arrays must be of the same length, unlike the zip function, which is more tolerant. For instance, over here I use the map function and illustrate an example. Reduce and folding. The map function collects the results of some function working on each and every element of an iterable object, such as an array of numbers. The reduce function does a similar job, but after every element has been seen and processed by the function, only one is left. The function should take two arguments and return one. The array is reduced by continual application so that just one is left. A simple example is to use the reduce to sum the numbers in an iterable object, which works like the built-in function sum. For example, reduce plus and passing the array from 1 to 10 returns the sum of them, which is 55. Internally, this does something similar to this. It sums 1 and 2, then sums the result of 1 and 2 with 3, and the result of that with 4, and so on. After each operation adding two numbers, a single number is carried over to the next iteration. This process reduces all the numbers to a single final result. A more useful example is when you want to apply a function to work on each consecutive pair in an iterable object. For example, here's a function that compares the length of two strings and returns the longer one. This can be used to find the longest word in a sentence by working through the string pair by pair. For example, we call the reduce function and pass the function that we've already defined, which is L, and as the second argument, we pass the array of these strings by using the split function and passing the string that we want to actually convert it to an array and check the results. You can see the longest word is the sentence word. Julia offers two related functions, fold L and fold R. These offer the same basic functionality as reduce. The differences are concerned with the direction in which the traversal occurs. In the simple summation example that we have shown, our best guess at what happened inside the reduce operation assumed that the first pair of elements were added first, followed by the second pair, and so on. However, It's also possible that reduce started at the end and worked towards the front. If it's important, use fold L from left to right and fold R for right to left. In many cases, the results are the same, but here's an example where you will get different results depending on which version you will use. However, if you want to use reduce and fold L or fold R functions for functions that take only one argument, use a dummy second argument. For example, over here reduce xy, which returns the square root of x. We pass the array from 1 to 4, and we actually pass a dummy argument also. As you can see, the result is 1.4 blah blah blah, which is equivalent to calling the square root function 4 times. Functions that return functions. You can treat Julia functions in the same way as any other Julia object, particularly when it comes to returning them as the result of other functions. For example, let's create a function making function. Inside this function, a function called new function is created, and this will raise its argument y to the number that was originally passed in as the argument x. This new function is returned as the value of create exponent function. Now we can construct lots of exponent making functions. First, let's build a squarer function and a cuber function. While we are at it, let's do a raised to the power of 4 function called quader, although I'm starting to struggle with the Latin and Greek naming. As you can see from the examples that I'm running, these are ordinary Julia functions. The definition of create exponent function above is perfectly valid Julia code, but it's not idiomatic. For one thing, the return value does not always need to be provided explicitly. The final evaluation is returned if return is not used. Also, in this case, the full form of function can be replaced with the shorter one-line version. This gives the concise version of the create exponent function. Function chaining and composition. Functions in Julia can be used in combination with each other. Function composition is when you apply 2 or more functions to arguments. You use the function composition operator O to compose the functions. You can type the composition operator at the REPL using \circ or circ, which is probably the short form for circ. For example, the square root function and the plus function can be composed like this, which actually, this composition actually adds the numbers first, then finds the square root. This example composes 3 functions, first, reverse, and uppercase, and we pass the composition of these functions to the map function as the first argument and an array of strings as the second argument by using a split function and passing in a sentence to it. Function chaining, sometimes called piping or using a pipe to send data to a subsequent function, is when you apply a function to the previous function's output. For example, over here I create an array from 1 to 10 and pass it to the sum function, then to the square root function, where the total produced by sum is passed to the square root function, obviously. The equivalent composition would be piping can send data to a function that accepts a single argument. If the function requires more than one argument, you may be able to use an anonymous function. Methods. A function can have one or more different methods of doing a similar job. Each method usually concentrates on doing the job for a particular type. Here's the function to check a longitude when you type in a location. The message generate function with one method. You see, if you define this in the REPL, tells you that there is currently one way you can call the check longitude one function. If you call this function and supply a number, it works fine. But what happens when you type in a longitude in say the format seen on the Google Maps. You see the method error no method matching is less in 64 and the string. The error tells us that the function has stopped because the concept of less than which we are using inside our function makes no sense if one argument is a string and the other a number. Strings are not less than or greater than integers because they are two different things, so the function fails at that point. Notice that the check longitude 1 function did start executing though. The argument LOC, that stands for location, could have been anything: a string, a floating point number, an integer, a symbol, or even an array. There are many ways for this function to fail. This is not the best way to write code. To fix the problem, we might be tempted to add code that tests the incoming values so the strings are handled differently. But Julia proposes a better alternative: methods and multiple dispatch. In the case where the longitude is supplied as a numeric value, the LOC or location argument is defined as being of type real. Let's start again and define a new function and do it properly. Now, this check longitude function does not even run if the value in LOC isn't a real number. The problems of what to do when the value is a string is avoided. With a type real, this particular method can be called with any argument provided that it is some kind of number. We can use the applicable function to test this. Applicable lets you know whether you can apply a function to an argument. That is, whether there is an available method for the function for arguments with that type. The false indicates that you cannot pass a string value to the check longitude function because there is no method for this function that accepts a string. Now the body of the function isn't even looked at. Julia does not know a method for calling check longitude function with a string argument. The obvious next step is to add another method for the check longitude function, only this time one that accepts a string argument. In this way, a function can be given a number of alternative methods, one for numeric arguments, one for the string arguments, and so on. Julia selects and runs one of the available methods depending on the types of arguments you provide to a function. This is actually multiple dispatch. Now the check longitude function has two methods. The code to run depends on the types of the argument you provide to the function, and you can avoid testing the types of arguments at the start of this function. Because Julia only dispatches the flow to the string handling method if LOC is a string. You can use the built-in methods function to find out how many methods you have defined for a particular function. As you can see, there is a large number of methods defined for the plus function. Obviously, something in matrix calculus and different libraries of linear algebra and etc. Julia chooses the most specific method to handle the types of arguments. In the case of check longitude, we have two specific methods, but we could define a more general method and specify the type of LOC as any. This method of check longitude is called when the LOC argument is neither a real number or a string. It's the most general method and won't be called at all if a more specific method is available. Type parameters in method definitions. It's possible to work with type information in method definitions. Here's a simple example. I define the function test and say that if the type of the argument that is passed to the test function is a subtype of real, then it is a valid argument and the function can actually process it. The test method automatically extracts the type of the single argument A passed to it and stores it in the variable t. For this function, the definition of t was where t is a subtype of real, so the type of t must be a subtype of the real type. It can be any real number, but not a complex number. T can be used like any other variable. In this method, it's just printed out using a string interpolation, and it doesn't have to be t, but it nearly always is. This mechanism is useful when you want to constrain the arguments of a particular method definition to be of a particular type. For example, the type of argument A must belong to a real number supertype. So this test method doesn't apply when A isn't a number, because then the type of the argument isn't a subtype of real. For example, I passed a string and I got an error. I passed an array, I got an error again, and the function test cannot handle this. Here's an example where you might want to write a method definition that applies to all one-dimensional integer arrays. It finds all the odd numbers in an array. But because of the way it's defined, it cannot be used for arrays of real numbers. For example, if I pass 10.0 as the last element of the list, we'll get an error. Note that in this simple example, because you are not using the type information inside the method definition, you might be better off sticking to the simpler way of defining methods by adding type information to the arguments. For example, I can define the findOdds function by specifying the type of the argument as an array of int64. But if you wanted to do things inside the method that depended on the types of the arguments, then the type parameters approach will be useful. If you are enjoying the content, don't forget to hit that like button and subscribe for more awesome videos. Your support means the world to me. In this tutorial, I'm going to talk about Julia Dictionary and Julia Set. Many of the functions introduced so far have been shown working on arrays and tuples. But arrays are just one type of collection. Julia also has other types of collections. A simple lookup table is a useful way of organizing many types of data. Given a single piece of information, such as a number, string, or symbol, called the key, what is the corresponding data value? For this purpose, Julia provides the dictionary object, called DICT or dict for short. It's an associative collection because it associates keys with values. Creating dictionaries. You can create a simple dictionary using the following syntax. The variable dict defined over here is now a dictionary. The keys are A, B, and C. The corresponding values are 1, 2, and 3. The equal greater than operator is now called the pair function. In a dictionary, keys are always unique. You can't have two keys with the same name. If you know the types of the keys and values in advance, you can and probably should specify them after the dict keyword in curly braces. You can also create dictionaries using the generator comprehension syntax. Use the following syntax to create a typed empty dictionary. Or you can omit the types and get an untyped dictionary. It's sometimes useful to create dictionary entries using a for loop. As you can see, in the for loop, I use the enumerate function, which returns the index of the list and the data that is contained in that index of the list. For example, in index 1 we have a.txt, in index 2 we have b.txt, and in index 3 we have c.txt. We have created a fvars dictionary and stored the key value pairs in this dictionary. This is one way you could create a set of variables stored in a dictionary. Looking things up. To get a value, if you have the key, you can use the following syntax. As you see, I assign a dictionary to dict variable and I use the key value to get the data that is stored in a dictionary. For example, I call dict A and I get the value 1. To get a value, if the keys are symbols, we use the following syntax. And if the keys are integers, we use something like this. You can use the get function and provide a fail-safe default value if there is no value for that particular key. If you don't want get to provide a default value, use a try-catch block. To change a value assigned to an existing key, we can use the following syntax. Keys. Keys must be unique for a dictionary. There is always only one key called A in this dictionary. By this dictionary, I mean the dict variable that we have already assigned a dictionary to in the previous section. So when you assign a value to a dictionary that already exists, you're not creating a new one, just modifying an existing one. To see if the dictionary contains a key, use hasKey function. To check for the existence of a key value pair, we use the following syntax. To add a new key and value to a dictionary, use the following syntax. You can delete a key from the dictionary using delete exclamation mark opening and closing parentheses, that is delete exclamation mark function. I call the dictionary to show its elements, and after that I apply the delete function. As you can see, the key and value of the D string as the key has been removed. You'll notice that the dictionary doesn't seem to be sorted in any way. At least, the keys are in no particular order. This is due to the way they are stored, and you can't sort them in place. To get all keys, use the keys function. The result is an iterator that has just one job, to iterate through a dictionary key by key. The syntax that I'm already typing, that is, I'm using the list comprehension for, that is, opening the bracket new element for loop variable in iterator, and each new element is collected into an array. An alternative also would be using the map function. That is, we use the map function, pass the uppercase function to it as the first argument, and as the second argument we pass the iterator, which is returned from the collect keys dict. Values of the dictionary. To retrieve all the values, use the values function. That is, pass the dictionary to the values function as the argument, and you'll get the values of the dictionary. If you want to go through a dictionary and process each key value, you can make use of the fact that dictionaries themselves are iterable objects. So you can use the for loop and iterate through the elements of the dictionary and print them one by one, where the kv variable is a tuple containing each key value pair in return. Or you could do for k in keys and pass the dictionary to it and print the key values. Even better, you can use a key value tuple to simplify the iteration even more. Here is another example where I iterate through a dictionary and put the elements of the dictionary in a tuple and print them one by one in each line. Notice the string interpolation operator, I mean the $sign. This allows you to use a variable's name in a string and get the variable's value when the string is printed. You can include any Julia expression in a string using $sign opening parentheses, putting the variable name and closing the parentheses. Sorting a dictionary. Because dictionaries don't store the keys in any particular order, you might want to output the dictionary to a sorted array to obtain the items in order. For example, over here I iterate through the iterable object which is returned by the sort function, and we pass to the sort function as an argument the collect keys dict. Sets in Julia. A set is a collection of elements just like an array or dictionary, with no duplicated elements. The two important differences between a set and other types of collection is that in a set you can have only one of each element, and in a set the order of elements is not important. whereas an array can have multiple copies of an element and their order is remembered. You can create an empty set using the set constructor function. As elsewhere in Julia, you can also specify the type of the elements inside the set. For example, over here I assign to the variable primes a set with elements of type int64. You can create and fill sets in one go by using the set and specifying the type, for example, a string over here, and putting, for example, the name of the colors inside it. You can also let the Julia guess the type of the elements inside the set. So it returns the set of type a string in this example, because we are passing the name of the colors, which are a string, to the set. Quite a few of the functions that work with arrays also work with sets. Adding elements to sets, for example, is a bit like adding elements to arrays. You can use push exclamation mark function. You can pass the sets variable name as the first argument to the push function, and as the second argument you can add the name of the element or the value of the element that you want to put inside the set. To see if something is in the set, you can use the in function. For example, in and the color green inside the colors set. If it returns true, it means that the green color or green string is inside the set as an element. There are some standard operations you can do with sets, namely find their union, intersection, and difference with the functions union, intersect, and set diff. For example, over here I define a set called rainbow that contains the colors of the rainbow. And then I use the functions union, intersect, and set diff to show the operations that you can perform on the sets. The union of two sets is the set of everything that is in one and the other set. The result is another set, so you can't have two yellows here, even though we've got a yellow in each set. So the elements are not repeated and they are unique inside the set. The intersection of two sets is the set that contains every element that belong to both sets. The difference between two sets is the set of elements that are in the first set but not in the second. This time, the order in which you apply the sets matters. The setDiff function finds the elements that are in the first set, I mean colors, but not in the second set, that is rainbow. Now we go back to the dictionaries. I've already defined two dictionaries, D1 and D2, and the operations union, intersect, and setDiff apply to dictionaries as well. There is also a merge function which can merge two dictionaries. Functions that work on arrays and sets sometimes work on dictionaries and other collections too. For example, some of the set operations can be applied to dictionaries, not just sets and arrays. Over here I define the dictionary D1. The findMin function can find the minimum value in a dictionary and return the value and its key. A string is a sequence of one or more characters usually found enclosed in double quotes. There are two important things you need to know about the strings. One is that they are immutable. You can't change them once they are created, but it's easy to make new strings from parts of existing ones. The second is that you have to be careful when using two specific characters, double quotes and $signs. If you want to include a double quote character in the string, it has to be preceded with a backslash. Otherwise, the rest of the string would be interpreted as Julia code, with potentially interesting results. And if you want to include a $sign in a string, that should also be prefaced by a backslash, because it's used for string interpolation. Strings can also be enclosed in triple quotes. This is useful because you can use ordinary double quotes inside the string without having to put backslashes before them. You will encounter a few specialized types of a string too, which consist of one or more characters immediately followed by the opening double quote. For example, I'll copy and paste some of them over here, which represent or indicate the regular expression or indicate a version of a string, or indicate a byte literal or a raw string that doesn't do interpolation. As you can see, you can use RVB or the keyword raw before the double quotes, opening double quotes and then closing double quotes to change the type of the string that you are putting in between the double quotes.
string interpolation. You often want to use the results of Julia expressions inside the strings. For example, suppose you want to say the value of x is n, and you'll type this in between the double quotes, as we have already learned. Where n is the current value of x, any Julia expression can be inserted into a string with the $, opening and closing parentheses construction. For example, I will define a variable called x and assign the value 42 to it, and I'll type the string above again, but this time I put the name of the variable in between $. As you can see, it prints the value of the variable name. You don't have to use parentheses if you're just using the name of a variable. For example, you can use the above string but without the parentheses, and it will work exactly like the command that we have already executed, as you can see. To include the result of a Julia expression in a string, enclose the expression in parentheses first, then precede it with a $. For example, I can type 2 plus 2 and evaluate the value of 2 plus 2 in between the opening and closing parentheses preceded by a $. Well, now we'll talk about substrings in Julia. Well, substrings in Julia, what is a substring? Basically, it's a smaller part of the string. To extract a smaller string from a string, we use the function getIndex, and we pass the string and the range that we want. And this is basically the syntax. I have already defined a string called s, and I'll give it a range and get a substring or part of the string. For example, 1 to end gives me the whole string, and 3 to 6 give me the word load. And I can change the range that I pass to the string, and I will get different parts of the string. And it's as simple as that. For example, over here, S3 till end minus 6 is equivalent to begin plus 2 till end minus 6. And both of them return the load of char or load of char. And this is actually a substring of the string that we've already defined. We also can use for loops to iterate through a string. But you have to watch out if you take a single element from the string rather than a string of length 1, that is with the same start and end positions, you'll get the character instead of a string. And we have to actually notice that, because it's a different type of thing that is returned. It's a character type. As you can see, one of them is ASCII character and the other one is a string of length 1. Not all strings are ASCII. To get access individual characters in Unicode strings, you can't always use simple indexing because some characters occupy more than one index position. Don't be fooled just because some of the index numbers appear to work. For example, I'll give you some examples which show you that it's not always going to work and it's not always a happy ending. For example, I define a string and a string variable su and assign some sort of string to it, and I will pass the range and test it one by one. One of them returns a character, the second index returns a character, but the third index actually is an invalid Unicode. It throws an Unicode error, as you will see. Instead of length str, using the function called length and passing the string to it. To find the length of a string, you can use the last index str. There is also a function called isASCII, which tests whether a string is ASCII or contains Unicode characters. For example, over here I can simply pass the su string that I've already defined and check whether it's ASCII or contains Unicode characters or not. For example, if I iterate through the string that I've already defined with the each index function, you can see the third character B starts with the fourth element in the string. You can also do this even more easily using the pairs function. and you'll see that the second character actually takes more space than the other ones. In this example, I will again use the each index iterator and iterate through the string, and I will show it with the macro show at show. There are other useful functions for actually working with strings like collect, this ind, next ind, and prevind, which gives the this index, next index, and previous index, and the collect function is one of the useful ones. I will give you an example, which returns an array of characters of the string, and you can iterate actually through this array, get the elements that you want. This ind function actually does something interesting, and if you run the code with this ind function, you'll see that it returns some indexes, actually index of the start of a character, and the following indexes for a specific character which actually takes up a particular size or a particular space, that index is actually repeated. And for example, over here 1, 2, 2, 4, 5, 5, 5, 5, 5, 9, and 10. Splitting and joining the strings. You can stick strings together, a process often called concatenation, using the multiply operator. For example, a string S multiplied by a string T gives you the combination or concatenation of them, which is ST. If you've used other programming languages, you might expect to use the addition operator, but that is not actually working, and it will throw you an error showing that the addition operator is not working in the Julia language. So use the multiplication operator. If you can multiply strings, you can also raise them to a power, obviously. And it gives you the repeated concatenation of a particular string. For example, s to the power of 18 gives you 18 times repeatedly the string s put together. You can also use the string function to concatenate two strings together. To split a string, use split function. Given a simple string that is s over here, we can use the split function to divide the string at the spaces, returning 5-piece array. Or you can specify the string of one or more characters to split at. The characters you use to do the splitting don't appear in the final result, and you have to notice that. If you want to split a string into separate single character strings, use the empty string, which splits the string between the characters. You can also split strings using a regular expression to define the splitting points. Use the spatial regex or regex, a string construction, or opening double quotes and closing double quotes. Inside this, you can use regular expression characters with spatial meaning. To understand what we have passed actually as a string into the regular expression type of string and passed it to the split function, you have to know the regular expression syntax, and that is the topic of a separate course. If you are interested in anything related to regular expression, just comment them down below the video so I will think about a future course. Here actually R, A, E, I, O, U, and there's a pipe character in between them, is a regular expression string. And as you'll know, if you love regular expressions, that is matches of any vowels. And so the resulting array consists of a string split at every vowel. Notice the empty strings in the results. If you do not want those, add a false flag at the end. You can actually join the elements of a split string in an array form using join function. Many functions in Julia let you use functions as a part of a function call. Anonymous functions are useful because you can make function calls which have smart choices built in. For example, split lets you provide a function in place of the delimiter character. In the next example, as you'll see,
The delimiter is bizarrely specified to be any uppercase character whose ASCII code is a multiple of 8. Above, we extracted smaller strings from larger strings. But when we extracted a single element from a string, we got something like single quotes and a character in between. In Julia, these are used to mark character objects. So, single quotation, a character name. Single quotation again is a character object, but double quotation, a character. Double quotation is a string with length 1. These are not equivalent. You can convert character objects to strings easily enough by using the string function and using the multiplication operator again and a string function and concatenating the characters together. It's easy to input 32 bits Unicode characters using \U escape sequence. The uppercase means 32 bits. The lowercase escape sequence \U small u can be used for 16 and 8-bit characters. Converting between numbers and strings. Turning integers into strings is the job of the string function. The keyword base lets you specify the number base for the conversion, which you can use to convert decimal digits to a binary, octal, or hexadecimal string. To convert the strings to numbers, use parse function, and you can also specify the number base, such as a binary or hex, if you want the string to be interpreted as using a number base. Converting characters to integers and back again. Int function with the capital I converts a string into an integer, and char or char with the capital C function turns an integer into a character. We can use both of these functions and show their usage. To go from a single character string to the code number, such as its ASCII or UTF code number, try this. For actually printing the alphabet quickly, we can use this one-liner. Printf formatting. If you're deeply attached to C-style printf functionality, you'll be able to use Julia macro. You call macros by prefacing them with the @. And the macro is provided in the printf package, which you'll need to load first. For example, I use using printf to load the printf package. After that, I use the @ and call the printf macro. I pass my string with a specific syntax and as the second argument the value of the pi. You can create another string using the sprintf macro, also to be found in the printf package. If you're curious about the %o.20f, this actually tells the styling of the sprintf and printf function to how to actually represent the pi value and how to print it. Convert a string to an array. To read from a string into an array, you can use the IO buffer function. This is available with a number of Julia functions, including printf. Here's a string data. It could have been read from a file. But I will actually assign a string data to the data variable. After that, we can read this string using functions such as readdlm. The read with delimiters actually function. Readdlm stands for read with delimiters. This can be found in the package delimited files. So for that, I import the package, load the package using the using keyword, using delimited files, and after that I call the readdlm package. And as the argument, I pass the IO buffer data to it. As a result, I get a 3x4 matrix, which is of type float64. You can add an optional type specification if you need to. For example, over here, I again call the function that I have called above, but as a second argument, I pass the int. So I get the elements of my matrix, 3x4 matrix, as an int64. Sometimes you want to do things to strings you can do better with arrays. Here's an example. Here I have assigned a path to the string variable s, and you can explode the path name string into an array of character objects using the collect function, which gathers the items in a collection or a string into an array. So if I call collect s, I will get an array which contains characters of the path that I've already specified. Similarly, you can use a split function to split the string and count the results. To count occurrences of a particular character object, you can use an anonymous function. For example, as the first argument, you can pass the anonymous function to the count function, and as the second argument, whatever is returned by the collect function. Although here converting to an array by the collect function is unnecessary and inefficient, here's the better way, actually passing the string itself as the second argument to the count function. Finding and replacing things inside the strings. If you want to know whether a string contains a specific character, use the general purpose in function. For example, I say in as the first argument I pass a character, and as the second argument I pass the string that I want to search inside. So the in function returns a Boolean value, true or false, whether a character is inside the string or not. For example, here I pass m as the first argument and s as the second argument. I get true because the m character is inside the string s that I've assigned to the variable s. But the occurs in function which accepts two strings is more generally useful because you can use substrings with one or more characters. Notice that you place the search term first, then the string you're looking at. Occurs in needle first argument as the first argument, haystack as the second argument, so you can remember it. Here are a couple of examples. You can get the location of the first occurrences or first occurrence of a substring using find first as the first argument needle and the second argument haystack. The first argument can be a single character, a string, or a regular expression. For example, I use the find first and use the string that I've already defined, that is the variable s as the second argument. And I'll get the range that the mer string is inside the string variable s. Here's another example using the isEqual function, which returns the first occurrence of character e inside the string s. In each case, the result contains the indices of the characters, if present. Replacing. The replace function returns a new string with substring of characters replaced with something else. For example, replace Sherlock Holmes with E that is actually converted to double E. And you can use the equal greater than operator to specify the pattern you're looking for and its replacement. Usually the third argument is another string, as here, but you can also supply a function that processes the result instead of actually using the equal greater than operator to assign something that you're looking for and its replacement together. Here I use the function uppercase instead of double E, and you can see that does its job. Actually capitalizes the characters that you're looking for. But the function here, the uppercase, actually is applied to the matching substring. Replacing using functions. Many functions in Julia allow you to supply functions as part of the function call, and you can make good use of anonymous functions for this. Here, for example, is how to use a function to provide random replacements in a replace function.
If you are enjoying the content, don't forget to hit that like button and subscribe for more awesome videos.
In this video tutorial, we talk about working with text files in Julia programming language. Reading from files. The standard approach for getting information from a text file is using open, read, and close functions. To read text from a file, first obtain a file handle. For actually opening a file and getting a file handle, first of all, we have to know our current directory. So I use the pwd function to find my current directory. Since I'm in the numerous folder, I have to go inside the IO folder where my io.jl file is located. So I'll use the cd function, which changes directory to the IO folder. After that, I'll use the open function to get a handle by opening a particular file. But before that, I have to use the touch function in order to create a txt file or the text file to actually get a handle from. F, also known as the file handle, is now Julia's connection to the file on disk. When you have finished with the file, you should close the connection using the close function. In general, the recommended way to work with a file in Julia is to wrap any file processing functions inside a do block. So I will use the open function do file and close the block. And I will do my stuff after opening the file in this block. The open file is automatically closed when this block finishes. Because of the scope of local variables in blocks, you might want to keep some information that was processed. For example, I can get the total time and total lines by actually opening a file inside the do block and get the information that I want. Over here, I define a variable called line counter to count the number of lines inside the numerous.txt file. In addition, I define a variable called time taken and use the elapsed macro. This way I can understand the total time taken to actually count the number of lines inside the numerous.txt file. Each line function actually returns an iterable which can be used to count the number of lines inside the numerous.txt file. Since the numerous.txt file has no lines, I'll add a couple of lines so we can continue the tutorial. Do not forget to hit that like button and subscribe to my channel. By helping me and subscribing to my channel, I can improve the quality of my content, since subscribing helps me to spend more time on the quality of my content. After adding the 2 lines, I'll test the code and read the lines again from the numerous.txt. As you can see, it shows a tuple. The first item is the time taken to read the 2 lines, and the second is the number of lines in numerous.txt. Reading a file all at once. To read a file all at once, I'll use the read function, pass as the second argument the type of thing that I want to read. You can check the documentation of the read function, but as you can see, I have passed the type a string, so I will read the lines inside the numerous.txt and assign them to the variable s. Also, I can use the do block to actually open the numerous.txt and read the files from it by using again the read function inside the do block. You can use read lines to read in the whole file as an array with each line and elements. As you can see, the lines variable is a vector with 2 elements, and the first element is actually the first line in the numerous.txt, and the second element is the second line in the numerous.txt file. After getting the lines and assigning them to the lines variable, we can actually iterate or step through the lines one by one and print them in each line with a counter. If I run the block, you see that the variable counter is not defined because I haven't actually run the counter equal to 1 code. So now the variable counter is defined, and the rerunning the block, you see that it works. The first line is subscribe to the numerous channel, and to the second line, I share tutorials with you so you can learn Julia programming language. So please guys, subscribe to my channel. We can actually read the file line by line. I will use the do block and open the numerous.txt file, and after that I will use the each line to get an iterable and do a for loop and print the length of each line and the line itself by using the printLine function. We can also use the enumerate function, which returns the number of the elements inside the array or an iterable, and also the content that is stored in that place. For example, I can use the enumerate function on an iterable object. You get the line numbering for free. As it is shown by the documentation, an enumerate function is an iterator that yields a tuple I and x, where I is a counter starting at 1 and x is the ith element or ith value from the given iterator. Another approach is to read until you reach the end of the file. You might want to keep track of which line you are on. So we use a while loop, and as the condition of the while loop, we'll use the EOF function, which stands for end of the file, and it checks whether we have reached the end of the file or not. And after that, inside the while block, we'll use the readLine function to read each line of the numerous.txt file. Also, if you have a specific function that you want to call on a file, you can use this alternative syntax. First of all, I will define the function that I want to call after opening a file. For example, over here I define the shout function, which actually reads the file and converts the case of the characters to an uppercase. After that, I'll use the open function and pass as the first argument the shout function and the second argument the name of the file. And it returns the shout version and assigns it to the shout version variable. You can see all the letters are uppercase now. Writing to files. To write to a text file in Julia programming language, we can open it using the W flag, which stands for write, and make sure that you have permission to create the file in the specified directory. Over here, I used the do block to actually open the file and pass the W flag, and use the write function and pass as the first argument the file handle, and as the second argument the content that I want to put inside the file. Over here, the subscribe.txt. If I run the block, you can see that I have written something to the subscribe.txt, and subscribe.txt is created. But as you can see, there's white space over there, or there are a couple of tabs. To remove the couple of tabs, I actually remove the tabs and add \n, which stands for new line, and run the code again. As you can see, the tabs are removed and the new line is added. Now I show you how to write 20 lines of 4 random numbers between 1 and 10 separated by commas. First of all, I create a function for random and return 4 random numbers by calling for random actually. So to do this, I'll open the file. I call the file for random numbers.txt and get the handle and pass W flag also, so the file will be created. I use a for loop inside the open block, do block, and actually get 4 random numbers by calling the for random function that I've already defined. After that, I'll write the 4 random numbers to a file and use the \, to add other 4 random numbers to the file in the new line. I'll do this 20 times. So I'll get, actually, since I haven't added the \n, you can see there's no new line. So I'll go back again and use the \, at the end of the write function, that the string that I have passed to the write function, and as you can see, we have 4 random numbers on each line, and it is repeated 20 times because I used the for loop from 1 to 20. But there is also a quicker alternative to do this. We can use the package delimited files and do this in one line. We'll use the write DLM function and pass as the first argument the name of the file, and as the second argument the rand function. Over here, I will use the for dlm_random.txt as my file name, and as the second argument, pass the random function and repeat that 20 times and get 4 random numbers each time. And as the last argument, I'll pass the delimiter that I want to use to separate the random numbers created. You see that it has done the same thing in one line.
If you are enjoying the content, don't forget to hit that like button and subscribe for more awesome videos.
Working with dates and times. Functions for working with dates and times are provided in the standard package dates. To use any of the time and date functions, you must do one of the following. Using dates or import dates. If you use import dates functions, you will need to prefix every function with an explicit date. For example, dates.dayofweek and passing the argument. However, if you add the line using dates to your code, this brings all exported dates functions into main, and they can be used without the dates dot prefix. Since we have typed using dates over here, we can use the now function without the dates dot prefix. Date, time, and date times. There are 3 main data types available. A dates.time object represents a precise moment of time in a day. It doesn't say anything about the day of the week or the year. It's accurate to a nanosecond. A dates.date object represents just a date, no time zones, no daylight saving issues, etc. It's accurate to a day. A dates.date time object is a combination of a date, a time of the day, and so it specifies an exact moment in time. It's accurate to a millisecond or so. Use one of these constructors to make the type of object you want. To convert the dates.now to time, we pass it to the dates.time function and assign it to the variable right now. To define the variable birthday, I pass a date to dates.date function. The dates.today function returns a date object for the current date. The dates.now function returns a datetime object for the current instant in time. Sometimes you want UTC the reference time for the world without local adjustments for daylight savings, so we can use the dates.now and pass the dates.utc to it as the argument. If we want to create an object from a formatted string, we use the datetime function in dates and supply a suitable formatted string that matches the formatting. As you observe, I provide different formatting strings. You can see what it does as it's passed as the second argument to the datetime function. Date and time queries. Once you have a datetime or date object, you can extract information from it with the following functions. For both date and datetime objects, you can obtain the year, month, day, and so on. Simply, most of the functions are self-explaining and it's obvious what their functionality is. Here you can pass the now function to the minute, second, and hour to get different parts of the time component. Even though the names are similar, they might have subtle differences in their functionality, so please check them out. As I'm running these lines of code, please do not forget to like, subscribe, and hit that bell notification button. Also, if you have any questions regarding the topic that I am explaining, please comment them down below the video. I will check them out and I will answer them as soon as possible. I also take requests to make special tutorials about special topics. So if you have any suggestions, I will be glad to hear it. There are 2 functions that we have already used, days of week in month and days of week of month. Days of week in month function tells you how many days there are in the month with the same day name as the specified day. Days of week of month tells us, for example, that the 15th of March 1997 was the 3rd Saturday of the month. Date arithmetic. You can do arithmetic on dates and datetime objects. Subtracting 2 dates or datetimes to find the difference is the most obvious one. For example, over here the convert function takes as the first argument dates.day and as the second argument a period of time. And it actually converts the period of time and outputs and returns something in terms of day. To add and subtract periods of time to date and datetime objects, use the dates.constructor functions to specify the period. Dates.year20 defines the period of 20 years. And dates.month6 defines a period of 6 months. So to add 20 years and 6 months to the birthday date, we have the code you see. To get the days to Christmas, we subtracted today's date from December 25th. To retrieve the value as a number, use the function dates.value. This works with different types of datetime objects too. Range of dates. You can make iterable range objects that define a range of dates. You can also use the filter function and pass as this first argument and second argument the anonymous function and the range of dates respectively. Similarly, here's a range of times 3 hours apart from now for a year. We define the variable d and assign the collect function which we have already passed a range of dates to it, and we get in return an array of elements which are of type datetime. If you have to pay a bill every 30 days starting on the 1st of January 2018, the following code shows how the due date creeps forward every month. We have used the for each function and passed as the first argument the anonymous function which prints date in a specific format, and as the second argument a range of dates starting from the 1st of the January 2018 till 1st of the January 2019. Date formatting. To specify date formats, you use date formatting codes in a formatting string. Each character refers to a datetime element. For example, a small letter y refers to year digit. A small letter m refers to month digit. And a small letter u represents the first 3 letters of the month name. And capital letter U represents the month name completely. And the list goes on and on. You can use these formatting strings with functions such as datetime and dates.format. For example, you create a datetime object from a string by identifying the different elements in the incoming string. Here we are using the date function and we are specifying a formatting string for our date. You can supply a formatted string to dates.format to format a date object. In the formatting string, you repeat the characters to control how years and days, for example, are output. When you are creating a formatted date, you can double some of the components of the formatted string to produce a leading 0 for single-digit date elements. Convert a date string from one format to another. You can use datetime function and a formatted string to convert the string to a datetime object. Then dateFormat function to output the object in a different format. If you are doing a lot of formatting, you can apply date functions to an array of strings. It's a good idea to predefine a date format object and then use that for bulk conversions. There are some built-in formats that you can use. For example, there is a dates.iso datetime format to give you the ISO 8601 format. And here is a good old RFC 1123 format. Date adjustments. Sometimes you want to find the date nearest to another. For example, the first day of that week or the last day of the month that contains that date. You can do this with the functions like dates.firstDayOfWeek and dates.lastDayOfMonth. So if we are currently in the middle of week, the first day of week is returned as you can see. We can also use the function chain operator to actually pass the arguments to functions. A more general solution is provided by the toFirst and toLast, toNext and toPrevious functions, or actually methods. With toNext and toPrev functions, you can provide possibly an anonymous function that returns true when a date has been correctly adjusted. With toFirst and toLast, you can find the first Sunday or Thursday or whatever of a month. Monday is first, Tuesday is second, and etc. Supply the keyword argument of is equal to year to get the first matching weekday of the year. Rounding dates and times. You can use round, floor, and ceil functions usually used to round numbers up or down to the nearest preferred values to adjust dates forward or backwards in time so that they have rounder values. Now we get the value of the variable birthday and use the ceil function which adjusts dates or times to forward in time. Moments in time. Date times are stored as milliseconds in the field instant. Use dates.value to obtain the value. For example, we define the variable moment and assign the dates.now to it and get the value by dates.value and passing the moment to it. If you use the more precise dates.time type, you can access nanoseconds. Timing and monitoring. The elapsed macro returns the number of seconds an expression took to evaluate. For example, I define the function test and pass the argument n to it and actually calculate the sign of a random number and assign it to the variable x inside the test function. After that, I will use the elapsed macro and pass the large value to the test function and calculate the time which has been taken in seconds to evaluate the result. The addTime macro tells you how long an expression took to evaluate and how much memory was allocated.
If you are enjoying the content, don't forget to hit that like button and subscribe for more awesome videos.
There are a number of different packages for plotting in Julia, and there is probably one to suit your needs and tastes. In this tutorial, I introduce you to Plots.jl package. There is a rationale behind choosing Plots.jl package for this tutorial. The most important reason for choosing Plots.jl package is it talks to many of the other plotting packages. Plots is a high-level plotting package that interfaces with other plotting packages, which here are referred to as backends. Those so-called backends act as graphics engines that produce the graphics. Each of these is also a standalone plotting package and can be used separately. But the advantage of using plots as the interface is, as you will see, a simpler and consistent interface. To get you up and running with the Plots.jl Julia package, first of all, we have to open up the VSCode in the project directory. And after that, we have to open up the Julia REPL. For opening the Julia REPL, we'll use the -- project equal to dot. As you know, dot refers to the current directory. After getting inside the REPL, we hit the right square bracket to go into the package mode. Then we type add plots and wait for the plots package to be installed. It takes roughly 10 to 20 minutes to install the package because it has to compile the package for the first time. And if you have a low spec computer, please go and pour a coffee and wait for the installation to finish. I fast forward the installation process. After installing the Plots package, we will use the using keyword to be able to use it in the Julia language. To be able to plot anything, we have to define a couple of functions. First of all, I'll define the fx function, and I use the plot to plot the f on the interval 0 to 2 pi. You can see the result of the plot in the VSCode pane at the right side. What if I want to plot more than one function? I actually can pass a list to the first argument of the plot function. For this, I define another function called gx and pass the g function as an argument to the plot function inside a list. I can also add a couple of other options to the plot function. For example, I can pass a title and I call it f and g plot, and I can also add x label and y label to the plot function. As you can see, the x and y labels are added to the horizontal and vertical axis. You can also modify the line width of the plot. We'll pass the keyword argument line width and change the value to something more than 1. If you notice, the plot looks a little bit ugly. Is there any way to change the look and feel of the plot? Of course there is. We can actually use the plot themes package. For that, I will go to the package mode in the Julia REPL by hitting the right square bracket and add the plot themes package. After the installation is finished, we can use the package, but before that I will explain something about the plot themes package. Here is the plot themes package GitHub page. Here we can find the information that we need to be able to use the package effectively. They have explained how we can use the package by adding it to the environment. They have also provided a list of themes that we can use, for example, Dark, Juno, ggplot to default, and the list goes on and on. Here's the line that you need to be able to use the theme provided by plot themes package. I copy this line for usage later. A couple of different plots for every theme is provided in this page. Now we paste the line we have copied from the GitHub page, but before that we have to import the plot themes package. Now I paste the line I copied, but I remove the keyword arguments because I don't need them for this tutorial, and actually change the first argument to something like Juno as provided in the plot themes GitHub page. Then I run the plot command again. As you see, the customized theme is working. I can also change the theme to something else like bright and test it again. Now we talk about different types of plots. First of all, let me rerun the commands that I've already used as an example. To use the scatter plot, we'll use the same setting but change the plot function to a scatter. Instead of getting smooth lines, we get a series of dots with gaps in between them. What if you want to plot a histogram? For that, we'll need a variable called x, for example, which contains a series of numbers, here from -20 to 20 and the steps 0.1 in between them. And I'll define two functions, x squared and cosine x, and I'll plot them again. I'll use the LW keyword, which stands for line width again. You can see the results in the VSCode pane and assign some labels to them. But if I want to plot a histogram, I will pass the y2 and y1 as the first arguments to histogram functions. Here I have also passed a label and a third argument called alpha. Alpha controls the transparency of our plot. If I change the alpha to 1, the plot becomes less transparent and darker. But if I change it to a value less than 1, it becomes more transparent. For plotting a three-dimensional surface, I'll define two ranges, x and y variables, and a Gaussian function. To actually get the type of the variables x and y, we can use the typeof function, which returns set range length. It gives us the information about the type of the variable. I also define a variable called gradient and assign the value returned by the cgrad function. Cgrad function takes a list of colors, and actually we can see the effect of the gradient on the surface plots. As a result of running the line, you'll see a color bar returned. And after that, we'll pass to the surface function xy and the function f and the color gradient as a keyword argument, and we'll get the surface that we want. Same as the other plots, I can assign x label, y label, and title to my surface plot. We can also use the plot3d function to plot parametric variables. Here the range t represents time, and x and y variables depend on t. We pass x, y, and t to plot3d function, specify the line width, the color, and the legend. If we put the legend false, we will not get the legend information, as you will see in the plots pane. Now I change the legend to true. The legend is added to the plot. If you found this tutorial helpful, please subscribe to my channel and like this video. Also, I constantly make new Julia programming tutorials, so check out my channel for more. In this tutorial, we want to talk about measuring the performance of our Julia code. As we know, the first step to understanding anything is to measure it. The same goes for writing high-performance Julia code. Whenever you care about the performance of your code, the time macro will end up being one of your most widely used commands on the Julia prompt. Built into the base Julia runtime, this macro wraps the provided expression to calculate and print the elapsed time while running it. It also measures and prints the amount of memory allocated while running that code. For example, for measuring the execution time of calculating the square root of random vectors of length 1000, we use the time macro, which prints the time taken in seconds and the amount of memory allocated while running that code. Since Julia is a just-in-time compiled language, this means that the Julia compiler and runtime compiles any Julia code into machine code the first time it sees it. This means that if you measure the execution time of any Julia expression that executes for the first time, you will end up measuring the time and memory use required compiling this code. So whenever you time any piece of Julia code, it's crucial to run it at least once prior to measuring the execution time. Always measure the second or later invocation. An enhanced version of the time macro is the timeve macro. This macro operates in a manner very similar to add time, but measures some additional memory statistics. As you can see, elapsed time, GC time, which stands for garbage collection time, and other useful information are displayed. The add time macro is used to time the execution of the square root function, and the result of that function is passed as an argument to the sum function. Elapsed macro is another built-in macro that that can be used to measure the execution time of Julia programs. Unlike the addTime and timev macros, which output the time information to the console, the elapsed macro returns the time in seconds as a result. This means that these resulting times can be used for further processing. For example, they can be used to assert performance limits during unit testing. For this purpose, I import the test library and use the test macro to compare whether the execution time of the input expression is less than 10 to the power of -5 or equal to it. Since I want to use the mean function, I import the statistics library. By the way, if you are enjoying the content, I constantly make Julia programming tutorials. Please like this video and also subscribe to the channel. Also, if you are new to Julia programming language, I have a Julia programming for beginners playlist. The link to the playlist is down in the description. In addition, if you have any questions, please comment them down below the video. Now I define a function that creates 1000 sets of 10,000 random numbers and then computes the mean of the squares for each set. We call the function once to ensure that all the code is compiled. Now I want to install another package called timer outputs and pass the name of the package to the pkg.add function. Once installed, the package can be loaded. Next, a global timer output object is created. This will store the results of our timing runs. Now we can time individual parts of the computation. We will reuse the random mean squared function we wrote previously. We annotate the code inside the function via the timeIt macro, which takes as an argument the time output object, a name to refer to each invocation, and the expression to be measured. Now we run the function random mean squared time and then view the timer outputs using the print timer function, which we passed it to object to it. The output nicely summarizes the timings for the nested calls and calculates the aggregates. For long simulations or complex optimization problems, this way of measuring timings can be very useful. The time macro is useful for identifying and investigating bottlenecks in our program. However, it's not very accurate in terms of fine-grained analysis of fast programs. If we want to, for example, compare two functions that take a few milliseconds to run, the amount of error and variability in the measurement will easily swamp the running time of this function. Then the solution would be to use the benchmarktools.jl package for statistically accurate benchmarking. Again, we use the package.add function to install the benchmark tools package. Here, instead of using addTime macro, we use the addBenchmark macro. Unlike addTime, however, this macro can only be used in front of function calls rather than any expression. It will evaluate the parameters of the function separately and then call the function multiple times to build up a sample of execution times. The output will show the mean time taken to run the code, but with statistically accurate upper and lower bounds. These statistics are estimated by evaluating the expression multiple times, with a number of evaluations determined in order to maximize the accuracy of the measurements. These estimates attempt to account for the noise inherent in running benchmarks on real machines. As an example, we measured the running time of creating a random array and calculating the square root of all of its elements. A simpler version of the output can be obtained by using the btime macro. This macro does the same operations as the benchmark macro, but provides simpler output that is similar to the basic time macro. Furthermore, it also returns the value of the expression that it evaluated. However, over here we are using the semicolon at the end of the line to suppress the output. Here is the timer outputs package GitHub page. They've already mentioned that its main functionality is the addTimeIt macro, similar to the addTime macro in base, except one also assigns a label to the quote section being timed. They've also provided example output and the instruction for using the package. Also, they have provided settings for printing. The package also provides additional features which are out of the scope of this tutorial. And also, here's the GitHub page for the benchmarktools.jl package. They provide a comprehensive guide on how to install the package, and they provide detailed documentation for the usage of the package. I've already explained the essential things that you need to know to use the benchmark.jl's package. If you don't want to miss out the future videos on the benchmarktools.jl package, please subscribe to my channel. As we have seen, macros are useful to measure the performance of individual expressions. But to fully understand how larger code bases perform, we need a profiler. The Julia runtime includes a built-in profiler which can be used to measure how long each line of code takes to run relative to a certain code base. It can therefore be used to identify bottlenecks in code, which can in turn be used to prioritize optimization efforts. In the Julia REPL, we use the right square bracket to go into the package mode and add the profile package to our Julia environment. This makes makes the add profile macro available. This measures and stores the performance profile of the expression supplied to it. Here again we define a function that creates 1000 sets of 10,000 random numbers and then compute the mean of the squares for each set. After calling the function once to ensure that all the code is compiled, we can run the profiler over this code as follows. This will execute the function while collecting profile information. The function will return as normal and the collected profile information will be stored in memory. The output from the profiler is a hierarchical list of code locations representing the call stack for the program. The number against each line counts the number of times this line was sampled by the profiler. Therefore, the higher the number, the greater the contribution of that line to the total runtime of the program. It indicates the time spent on the line and all its callees. If the hierarchy is too deeply nested, thereby making the output confusing, you can get a flat output by calling profile.print and specify a format, for example flat. In addition, in order to profile a different program during a Julia session that is already running, it may be necessary to clear the stored profile from memory. The profile.clear function does this and must therefore be run between any two invocations of add_profile within the same Julia process. There are some packages that provide graphical user interface for seeing the output of the profiler. However, at the time of recording this video, most of these packages are full of bugs and they are not cross-platform. To wrap up this tutorial, the two macros @benchmark and @btime should be your standard method to measure performance in Julia. In rare cases, such as for long-running programs that take too long and cannot be executed multiple times, you may fall back to the @time macro. However, such occasions should be rare. Don't forget to like this video and subscribe to my channel for future Julia programming tutorials. In this tutorial, I'm going to show you guys how to develop a package in Julia like a boss. This package can be anything like a scientific computing related package or whatever related to software development. Not only I show you a practical way to develop a package in Julia, but also I talk about continuous integration and testing. Specifically, I cover the GitHub Actions and code coverage. You can pretty much ignore that and just focus on the package development part. First of all, you have to sign up on the CodeCov website. I put the link down in the description of the video. You have to sign up and sign into with GitHub. You may need to provide permissions for CodeCov to access GitHub. After you sign into the GitHub, you have to set up your repository. I will show that later in the video. Next, open up your VSCode in a directory that you want to put your package into. Open up your terminal on Linux or your command prompt on Windows and type Julia. Hit the right square bracket and go into the package mode and type add pkg templates space revise. Make sure you add these packages in the global environment of the Julia. By the way, don't forget to hit that like button and subscribe to my channel for more tutorials on Julia programming. After the installation has finished, hit the backspace to go into the REPL, load the pkg templates package inside the REPL with the help of using keyword. Then we call the template function and pass the required arguments for our package to it. I put this chunk of code in the video description so you can copy and paste it. Don't forget to pass the correct Julia version and your GitHub username to the template function. After defining the variable t, now we can pass the name of our package to it. A directory with the name of our package will be created in the current directory. Now we change our directory to the package directory and open up the VSCode in the package directory. Now it's time to go into your GitHub account and create a repository with the name of your package that you've already specified, ending with .jl. Leave the boxes related to readme.md, license, and .gitignore unchecked, since these are handled by pkg templates package. I assume that you have properly set up your GitHub account on your computer. You have set your username and password, and just commit the package files and push them to GitHub. Here you see the GitHub repository after pushing the files to GitHub. You see two badges, one of them is related to continuous integration and the other one to the code coverage. Now I show you how to add your current package that you've already created to the global environment of Julia, so you can use the using keyword and load the package inside Julia REPL or any other project on your computer. Basically, you open up the Julia REPL and go into the package mode and type activate to actually activate the global environment. You can use the SD command to see the current installed packages in your global environment. Then type dev dot to add the current package to the global environment. Make sure that you have already set up the revise package. For configuring the revise package for both Windows and Linux operating systems, you can check the revise documentation. Make sure that you have copied the code specified in the revise documentation and pasted it in the startup.jl file. Now let's take a look at the files created by the pkg templates package. In the src directory, there is a file with the same name as your package name. You put your package code inside this file. In the tests directory, there is a file named runtests.jl. You put your unit integration and regression tests for your project inside this file. Manifest.toml and project.toml files contain the dependencies of your project. Specifically, the project.toml file contains a list of dependencies and the manifest.toml specifies their exact versions and subdependencies. In the .github folder and going into the workflows directory, you'll see a ci.yaml file which contains the information for the continuous integration and GitHub actions. We will modify this file later for configuring the code coverage. To develop a package, I go inside the src directory and open up the myproject.jl file. Inside this file, I write my package code. For example, I write a function named operate on xy. I set default values for x, y, and return the multiplication of x and y. Now I open up my REPL and check whether I'm inside the global environment and use the using keyword to load the package inside the global environment in the Julia REPL. After calling the operate on xy function with the default arguments, I get the 2 as a result, since I have set x to 1 and y to 2. Now I add an extra line to the operate on xy function, for example print line and some string, and call the operate on xy function again to see whether the function gets precompiled and changed on the fly by the revise package. If I hadn't installed the revise package, I had to select the new definition of the function again and hit the shift enter to actually run the function definition in the REPL, then call the operate on xy function. Also note that the revise package only detects changes made inside the myproject.jl file, which is in the src directory, and the revise package does not actually detect any changes made in the tests directory. Now we can load the test package by using the using keyword, and after that use the add test macro and check whether the result returned by the operate on xy function is equal to 2. As you can see, the test has passed. But if I change the expected result to some value other than 2, for example 3, we see that test failed. Now we go inside the runtests.jl file. We can put the code that we have already run in the REPL inside the runtests.jl file. Note that you have to load your package and the test package inside the runtests.jl file by selecting those using keywords and hitting the shift enter. You can also run the whole test set inside the Julia REPL by going inside the package mode and typing test. But if you are not in the package environment but the global environment, you can go inside the package mode and type test your package name or test my project over here. Now we commit the changes that we have already made to our package and push them to GitHub. After pushing the code, you'll notice that the commit is now on the server, but also that a small orange circle is next to the commit. This shows that a GitHub action is executing based on that push to the main branch. You can see these actions in progress on the Actions tab, where the action may be complete by the time you open it. If you further click on one of the jobs and select the Julia run test, you can see the output on the server. It ran your test suite on its isolated environment and is showing a check mark because the tests passed. As you can see, the CI badge or continuous integration badge on the GitHub page is showing passing, but the code coverage is not yet active. Since we have set up our repository for our package, we'll set up the repository in the code coverage website. As a result of setting up our repository, we'll be given a code coverage token. We also have to copy and paste a chunk of YAML script inside the ci.yaml file that our package already contains. First of all, we'll click on the repository secret link and we'll be redirected to our GitHub page to create a repository secret. Over here, we paste the code coverage token that is given to us by the CodeCov website. Now we copy this chunk of code inside the ci.yaml file. Finally, we push the changes that we have made to the GitHub. On the GitHub page, as you can see, the code coverage badge is active and 100%. And 100% because we had one function and one test for that function, so our test covers the functionality of our package. Don't forget to hit that like button and subscribe to my channel, since I constantly make Julia programming tutorials. And if you are a beginner, I've got a Julia Programming for Beginners playlist, so don't forget to subscribe to not lose this content. In this tutorial, I talk about two main concepts, macros and metaprogramming. If you have watched my Julia Programming for Beginners playlist, you know that we have talked about macros several times, but we haven't discussed the very nature of them. But before that, I have to give you the definition of metaprogramming. What is metaprogramming? Metaprogramming is when you write Julia code to process and modify Julia code. With the metaprogramming tools, you can write Julia code that modifies other parts of your source files and control under what condition and when the modified code runs. The execution of raw source code in Julia programming language takes place in several stages, but for the simplicity in this tutorial, we consider two stages. The first stage is when your raw Julia code is paused, converted into a form that is suitable for evaluation. This is actually the phase when all your syntax mistakes are noticed. The result of this stage is an abstract syntax tree, or AST for short. Stage 2 is when that paused code is executed. When you run a Julia code in the REPL or from the command line, you don't notice the two stages because they happen so quickly. However, here's the important part. With Julia's metaprogramming facilities, you can access the code after it has been paused but before it's evaluated. This lets you do things that you can't normally do. For example, you can convert simple expressions to more complicated expressions, or examine code before it runs and change it so that it runs faster. Any code that you intercept and modify using these metaprogramming tools will eventually be evaluated in the usual way, running as fast as ordinary Julia code. One example of metaprogramming is the time macro that we have already used in our course. The addTime macro inserts a start a stopwatch command at the beginning of the code and adds some code at the end to stop the stopwatch and calculate the elapsed time and memory usage. The modified code is then passed on for evaluation. Another one is the @which macro. The macro does not allow the expression 2 plus 2 to be evaluated at all. Instead, it reports which method would be used for these particular arguments, and it also tells you the source file that contains the method's definition and the line number. Now I want to talk about the quoted expressions. For metaprogramming to be possible, there has to be a way for Julia to store an unevaluated but paused expression as soon as the pausing phase has finished. This is the colon prefix operator. To Julia, the colon x is an unevaluated or quoted symbol. Here I assign the value 3 to the variable x, but the colon x returns the x symbol. To quote whole expressions rather than individual symbols, start with a colon and then enclose the Julia expressions in parentheses. There is an alternative form of the colon opening and closing parentheses construction that uses the quote and keywords to enclose and quote an expression. Here I assign value returned by quoting for loop to the expression variable. The expression object is of type expr. As you can see, it's paused and it's ready to go. Now the question is, how do we evaluate the expressions? We can use the eval function for evaluating an unevaluated expression. For instance, we can use Julia's eval function and pass the colon x to it. Basically, we can pass any quoted expression to the eval function and it will be evaluated. With these tools, it's possible to create any expression and store it without having it evaluate. More usefully, it's possible to modify the contents of the expression before it's evaluated. As I said, we can modify an unevaluated expression. Consider the value assigned to the variable p. Notice the helpful line numbers that have been added to each line of the quoted expression. The labels for each line are added on the end of the previous line. We can use the field names function to see what's inside this expression. The head field is column block. The args field is an array containing expressions including comments. We can examine these with the usual Julia techniques. For example, what's the second sub-expression? And print them out. As you can see, the expression p contains a number of sub-expressions. We can modify this expression quite easily. For example, we can change the last line of the expression to use prod function rather than sum function, so that when p is evaluated, it will return the product rather than the sum of the variables. Alternatively, you can target the sum function directly by borrowing into the expression. Once the code has been paused, we have the abstract syntax tree. It's a nested hierarchical structure that's designed to allow both you and Julia to easily process and modify the code. The dump function lets you easily visualize the hierarchical nature of an expression. For example, the expression colon 3 times sine of pi over 2 is represented like this. You can see that the AST consists entirely of expressions or EXPRs and atoms, for example, symbols and numbers. In a way, strings and expressions are similar. Any Julia code they happen to contain is usually unevaluated, but you can have some of the code evaluated using interpolation. I've already talked about how to use a string interpolation operator in the Julia Programming for Beginners playlist. Indeed, the $sign, when used inside a string and possibly with parentheses to enclose the expression, this evaluates the Julia code and inserts the resulting value into the string at that point. For example, the sign of 1 is $sign of 1. The $sign of 1 will be evaluated to its value. In just the same way, you can use the $sign to include the results of executing Julia code interpolated into an expression which is otherwise unevaluated. For example, code S is equal to $sign of 1 plus cosine of 1, and we end it with the end keyword. Even though this is a quoted expression and hence unevaluated, the value of sine of 1 plus cosine of 1 was calculated and inserted into the expression, replacing the original code. This operation is called splicing. Once you know how to create and handle unevaluated Julia expressions, you'll want to know how you can modify them. A macro is a way of generating a new output expression given an unevaluated input expression. When your Julia program runs, it first pauses and evaluates the macros, and the processed code produced by the macro is eventually evaluated like an ordinary expression. Here's the definition of a simple macro that prints out the contents of the thing you pass to it, and then returns the expression to the calling environment, here the REPL. The syntax is very similar to the way you define functions. You run the macros by preceding the name with the @ prefix. This macro is expecting a single argument. You are providing unevaluated Julia code. You don't have to enclose it with parentheses like you do for function arguments. First, let's call this with a single numeric argument, for instance @p, and pass the number 3. Since numbers are not expressions, the if condition inside the macro didn't apply. All the macro did was return n, which is the number 3. But if you pass an expression, the code in the macro has the opportunity to inspect and process the expression's content before it's evaluated using the .args field. There is an eval function and an @eval macro. You might be wondering what's the difference between the two. The function version eval expands the expression and evaluates it. The macro version does not expand the expression you supply to it automatically, but you can use the interpolation syntax to evaluate the expression and pass it to the macro. Here's an example where you might want to create some variables using some automation. We'll create the first 10 squares and 10 cubes, first using eval function, which creates a load of variables named var _squares _n, which n iterates through 1 to 10. Alternatively, we can use the @eval macro, which similarly creates a load of variables named var _cubes _n. You might want to use a one-liner once you feel confident, which basically does the same thing as the code above. When you use macros, you have to keep an eye out for scoping issues. In the previous example, the $ESC passing the variable EX to its syntax was used to prevent the expression from being evaluated in the wrong context. Here is another contrived example to illustrate this point. This macro declares a variable S and returns a quoted expression containing S and an escaped version of S. When we run the macro and pass the value to, you can see that the macro returned different values for the symbol S. The first was the value inside the macro's context for, the second was an escaped version of S. That was evaluated in the calling context where S has the value 0. In a sense, esc function has protected the value of S as it passes unharmed through the macro. To see what the macro expands to just before it's finally executed, we use the macro expand function. It expects a quoted expression containing one or more macro calls, which are then expanded into proper Julia code for you so that you can see what the macro would do when called. Here I've written another macro do times, which adds do times construction to the language, which can be used like this. If you use the macro expand function on this, you can see what happens to the symbol names. I constantly make Julia programming tutorials. Please like this video and subscribe to my channel to not lose the future content. Also, don't forget to look at the playlists on my channel. You can find the link to them in the video description. In this tutorial, I show you how to install Pluto.jl in Julia. Pluto is a Julia-specific package equivalent to Jupyter Notebook in Python. However, it has its own special features. After the installation of Pluto package, I talk about its general usage in Julia. To install the Pluto package, you have to open up the Julia REPL. Make sure everything is working correctly. In the Julia REPL, hit the right square bracket to go into the package mode. To install the Pluto package, type add Pluto in package mode in Julia REPL. Then you have to wait for the installation to finish. Depending on your system specifics and your internet connection, it might take some time, so pour some coffee and wait for it. After the Pluto package is added to our Julia environment, we can hit backspace to get out of the package mode. You can hit Ctrl L at the same time to clean up the REPL output. Now type import Pluto to import Pluto package in our Julia REPL. A message is shown saying that start a notebook server using Pluto.run. So we type Pluto.run in the REPL. A message is shown giving us an address which is on the local host, but depending on your system you might get another URL. Whatever your URL is, make sure to copy and append the question mark secret to whatever URL you are given. Or if you are using the local host, simply click on the local host link given. Now in your browser you will see some environment similar to Jupyter Notebook. There are some featured notebooks in this page that you can scroll and click on whichever you like to learn something about the Pluto.jl package. From visualization to image processing, plotting functions, machine learning, and whatever you like. To open up a new notebook, click on Create a new notebook. This is the Pluto.jl package environment. It's just a notebook that you type some commands and get some output instantly. For example, I can type some message like print this is numerist. To run this line of code, I go to the bottom right corner and click on that button, or I can hit Shift Enter. You can also see some information at the bottom right showing the time it's taken to run the command in microseconds. You can click on the eye at the top left to show or hide the code block. You can also click on the plus button or hit Ctrl Enter to add a new cell. Now I type print and print an important message in this cell. Then I hit Shift Enter to see whether it works. You can also delete a cell by clicking on the three dots on the top right corner and clicking on Delete Cell. After hitting Delete Cell at the bottom left corner of the page, you can see that you can undo deleted cell by clicking on Undo. To save your notebook, you can go at the top of the page and type the name of your notebook file. Then you click on the Choose and the notebook will be saved. You can also export your Pluto notebook in different formats by clicking on the Export button. You can export it as a notebook file, a static HTML, PDF, and you can also record any changes you make to your notebook. At the bottom right corner, you can go to the Live Docs to check out documentation for different commands in the Julia. And of course, the documentation provides some examples for the commands that you want to use, or click on status to see some benchmarks related to your Pluto notebook. You can click on the status again to hide this section. Don't forget to like this video and subscribe to my channel to not lose future content on Julia programming language. Also check out my Julia Programming for Beginners playlist. The Julia's data frames package is an alternative to Python's pandas package, but can be used with pandas using the pandas.jl wrapper package. First of all, we have to open the Julia REPL, and after that, hit the right square bracket to go into the package mode, then type add data frames. Then all you have to do is to wait for the Julia to add the data frames package to your Julia environment. Depending on your computer, adding the package may take some time, so pour some coffee and wait for it. After the data frames package has been successfully installed, it's time to add the CSV package, so I type add CSV and wait for the package to be installed. After the CSV package is installed successfully, I clean up the output of the REPL by hitting Ctrl L at the same time, then type using data frames to check whether the package loads successfully, and also type using CSV to check whether the CSV package is installed successfully. Now it's time to use the actual data frames package. There are a few different ways to create new data frames. For this introduction, the quickest way to load the anscom dataset and assign it to a variable anscom is to copy-paste several rows of data, convert them to an array, and then rename the column names like this. Anscom's quartet comprises 4 datasets that have nearly identical simple descriptive statistics, yet have very different distributions and appear very different when graphed. Each dataset consists of 11 xy points as a tuple. You can create simple data frames by providing the information about rows and column names in an arrays. To create a completely empty data frame, you can supply the column names Julia symbols and define their types, remembering that the columns are arrays. For example, I use the VSCode function to add data to my empty data frame that I have already defined as df. You can get the type of the anscom variable by using the typeof function, which returns data frame as the type. To obtain a list of column names, use the names function. Other useful function is the size, which returns the number of rows and number of columns. The describe function provides a quick overview of each column. Notice that some of the columns, all the x columns, contain integer values, and others, all the y columns, are floating point numbers. Every element in a column of a data frame has the same data type, but different columns can have different types. This makes the data frame ideal for storing tabular data, strings in one column, numeric values in another, and so on. There are various ways to select columns. You can use the dot or period, the standard Julia field accessor. For example, anscom.y2 returns the column y2. Or you can use the general Julia convention for symbol names. Precede the column names with a colon, so column y2 refers to the column called y2 or column number 6. You can use integers and vectors of integers. Here's the 6th column, all rows of the anscom's data frame. And here are columns 1, 2, 3, 5, and 8. Here are the first x and y columns. You can supply a regular expression to grab a set of matching column names. Here's the result showing all the columns whose names end in a 2. To access the 3rd and 5th columns of the dataset anscom, you can use any of the following. You can also access the columns using variables. For example, if a is equal to x3 and b is equal to y1, then we have to take rectangular slices. For example, we can use anscoms 4 to 6 as the first argument and x2 to x4 as the second argument. By passing that range and that list, we get the selected rows and columns. Instead of range of rows, you can also specify individual rows using commas. And of course, you can use the index numbers. To specify a range of rows and columns, use index numbers. Also notice that the row numbering for the return data frames is different. Rows 4, 5, and 6 became rows 1, 2, 3 in the new data frame. As with arrays, use the colon on its own to specify all columns or rows when you want to view the contents. When you are modifying the contents, the syntax is different, as described later. So to see rows 4, 6, 8, and 11 showing all columns, and for all rows, columns x1 and y1 we have, you can select all the rows of a data frame where the elements satisfy one or more conditions. Here's how to select rows where the value of the element in column y1 is greater than 7. The inner phrase anscom.y1.greater than 7.0 carries out an element-wise comparison of the values in column y1 and returns an array of boolean true or false values, one for each row. Notice the broadcasting operator dot. These are then used to select rows from the data frame. It's as if you had entered anscom and passing a list of true or false values as the first argument and colon as the second argument. So the code on line 81 and the code on line 83 are equivalent. That is, the comparison operator on line 81 will be converted to a list of true or false values. In a similar way, here is a result that contains every row where the value of the number in column y1 is greater than that in column y2. Another way to select matching rows is to use the Julia function filter. Combining 2 or more conditions is also possible. Here is a result consisting of rows where the value of y1 is greater than 5 and that of y2 is less than 7. An equivalent using filter function would be: here I import a statistics package by running the using statistics. You can apply a function to a column. To find out the mean of the values in the column named x2, we use mean and pass the anscom.x2 to it. The data frames package provides 2 convenient utilities, each call function and each row function. These can be used for iterating through every column or every row. Each value is a tuple of symbol, column heading, and data array. To apply the mean function to every column of the data frame, you can either use a comprehension, which returns a new array containing the mean values for each column. Alternatively, you can use a broadcasted version, that is mean dot and pass the each column, and inside the each column pass the anscom. Similarly, you can use the each row function to actually iterate through each row. For instance, in this dataset, each element of each row is a number, so we could, if we want to, use each row function to find the meaningless mean of each row. Now let's shift our focus to statistics. The built-in describe function lets you quickly calculate the statistical properties of the columns of a dataset. Supply the symbols for the properties you want to know, choosing from the mean, standard deviation, minimum, Q25, median, Q75, max, L-type, N unique, first, last, and N missing. We can also compare the XY datasets too. We can use the core function for the correlation. For instance, let's look at the correlation between XY datasets. Notice how similar these correlations are. x1, y1 is the same as x2, y2, x3, y3, and x4, y4. Each of the 4 datasets has the same mean, median, standard deviation, and correlation coefficient between x and y. Judging by the simple summary statistics, you would think that they were pretty similar. Let's plot them. Anscombe's quartet comprises 4 datasets that have nearly identical simple statistical properties, but are actually very different. Each dataset consists of 11 xy points. They were carefully constructed in 1973 by the statistician Francis Anscombe to demonstrate both the importance of looking at your data and of graphing that data before relying on the summary statistics and the effect of outliers on statistical properties. The first appears to show a simple linear relationship corresponding to 2 variables correlated and following the assumption of normality. The second set of points is not distributed normally. There is an obvious relationship between the 2 variables, but it isn't linear and the Pearson correlation coefficient is not really relevant. In the third set, the distribution is linear but with a different regression line, which is offset by the one outlier which exerts enough influence to alter the regression line and lower the correlation coefficient from 1 to 0.816. Finally, the fourth set shows an example when an outlier is enough to produce a high correlation coefficient, even though the relationship between the 2 variables is not linear. The quartet is still often used to illustrate the importance of looking at a set of data graphically before starting to analyze according to a particular type of relationship, and the inadequacy of basic statistic properties for describing realistic datasets. If you want to find a linear regression line for the datasets, you can turn to the GLM Generalized Linear Models package. Using GLM and Stats model, we add these packages to the Julia environment. To create a linear model, you must specify a formula using addFormula macro, supplying the column names and the name of the data frame. The result is a regression model. Useful functions in the GLM package for working with linear models include summary function and coef function, which stands for coefficient. The coef function returns the 2 useful coefficients that define the regression line, the estimated intercept and the estimated slope. After getting these 2 values, it's easy to produce a function for the regression line in the form of y is equal to ax plus c. After defining the function f for describing the regression line, it can be drawn in a plot. Here we plot the first series and add a plot of the function fx with x running from 2 to 20. See how it compares with the smoothing line we used earlier. Not all datasets are as consistent and tidy as the examples that we have provided. It's possible that you'll read some data into a data frame only to discover that it's got a few problems with inconsistently formatted or missing elements. Here we'll create a simple test data frame by hand, defining the columns one by one. It's a short extract from what might be a periodic table. We can use the describe function to find information about our data frame. To add a column, we can use the hcat function, which adds another column of integers which will be called colon x1 from 1 to n. This creates a copy of the data frame and we haven't changed p-table or assigned the new data frame to a symbol. Instead, let's add melting and boiling points of our chosen elements to the table. I represent the data with MP and BP for melting points and boiling points. Notice the use of different syntax to access columns when changing them. If you just want to look at values, you can use left square bracket column, comma, your column name, right square bracket, which provides you with a read-only view of the data frame. If you want to change the values, use left square bracket, exclamation mark, comma, your column name, right square bracket. The exclamation is the usual Julian clue that indicates function that might modify the data arguments. To illustrate how to create a new column based on things in the other columns, we'll add a column called liquid showing for how many degrees of Celsius an element remains liquid, that is boiling points dash melting points. To add or replace a column of a data frame with another column of data, that is an array of the right length, use access function or the map function, as shown on the line 192 and 194. You can also use rename exclamation mark function to rename columns. There is also a rename function without the exclamation mark, which doesn't change the original data frame. The select exclamation mark function creates a new data frame that contains the selected columns. So to delete columns, use select exclamation mark together with not, which deselects a column that you don't want to include. It's easy to add rows. Use push exclamation mark with suitable data of the right length and type. Those missing values should be replaced soon using the functions from earlier. We can locate the new element by name and change the value for liquid like this. Or we could use the atomic number to obtain access to the right row and do it that way. To delete rows, use the delete exclamation mark function with one or more row specifiers. Alternatively, you could delete rows by specifying a condition. For example, to keep rows where the boiling point is less than 100 Celsius, you could just find the rows that are greater than or equal to 100 Celsius, then assign a variable to keep the result. To find values, the basic idea is to use an element while operator or function that examines all rows and returns an array of Boolean values to indicate where each cell meets to the criteria for each row. For instance, we can use ptable column melt less than 100 to get a 6-element bit array, then use this Boolean array to select the rows. You could use this to return rows where a value in a column matches a regular expression, and you can edit the elements in the same way. You can also find matching entries by using a recursive function with the dot operator. To investigate subsets and groupings, let's recreate the data frame ptable again and add another column. This column gives the state of each element at room temperature. It's now possible to collect up and group the elements according to their state. The group by function splits the original data frame into grouped data frames according to the values in the named column. For example, with 3 elements that are gases at room temperature and the others which are solid, we can obtain 2 grouped data frames. Here we are saving the grouped data frame in GD variable. The combine function lets you group the rows and then apply a function to one of the fields of every row in the group. We find the mean melting point of all the gases and the mean melting point of all the solid elements, and we are using the group data frame again. The sort exclamation mark function works with data frames as well. You supply the columns on which to sort using the following syntax: sort exclamation mark and pass the ptable. The resulting data frame is sorted first by its state at room temperature, so gas before solid, then by its atomic weight, so iron before copper. Don't forget to like this video and subscribe to my channel to not lose future content on Julia programming. Also check out my Julia Programming for Beginners playlist. What is the best library or package to plot in Julia programming language? Among the various options available, such as Pluto.jl, Mackie or Mackie.jl package is among the best libraries to plot in Julia. It can easily be considered the matplotlib of Julia programming language, Swiss Army knife of visualization or plotting because of its capability and versatility. If you are looking for a powerful package in Julia programming language to visualize your research results, look no further than Mackie package or Mackie library. Mackie visualization package has 3 main backends: Cairo Mackie, GL Mackie, WGL Mackie. These 3 backends serve different purposes. But before discussing that, open up the Julia REPL, hit the right square bracket to go into the package mode, and type add Cairo Mackie. This adds Cairo Mackie package to your Julia environment. Depending on your operating system, adding the package might take some time, so pour some coffee and wait for it. As I've already said, Mackie is the name of the whole plotting ecosystem, and Mackie.jl is the main package that describes how plots work. Cairo Mackie is used to render vector graphics and high quality 2D images. GL Mackie is used for interactive windows and true rendering. And finally, WGL Mackie is similar to GL Mackie but works in web browsers, not native Windows. Since we have already added the Cairo Mackie package to our Julia environment, we can use the using keyword and type using Cairo Mackie to import the Cairo Mackie package. To plot anything in Julia programming language using Mackie, we need a figure object. So we create a figure and give it a background color other than the default white so we can see it. Basically, returning a figure from an expression will display it if your coding environment can show images. Here I specify the background color with the tomato symbol. Another common thing to do is to give a figure a different size. The default is 800 times 600. So I pass a tuple of width and height to the size argument, and what you get is a figure of a specified size. The most common object you can add to a figure which you need for most plotting is the axis. For this purpose, we specify a position in the figure's layout as the first argument. Here I have specified the position 1, 1, which stands for the number of rows and columns. You can change the number of rows from 1 to 2 to see the effect. The default axis has no title or labels. You can pass those as keyword arguments. Here I have specified the title, X label and Y label. So now that we have an axis, we are ready to actually plot something into an axis. Here I have used the Mackie's lines plotting function to plot the sine function into an axis by passing it as the first argument. By changing the lines function to a scatter function, we can get a scatter plot. It works very similar to lines function but shows separate markers for each input point. If you don't want to explicitly create figure and axis for every plot that you make, you can use the lines function without the exclamation mark or a scatter function without the exclamation mark. For instance, lines function with exclamation mark mutates an existing axis. Lines function without the exclamation mark creates an implicit one. The same holds for the scatter function and so on. If you want to specify a different resolution for your scatter plot or set an axis title and labels, you can pass a special keyword arguments to it called axis and figure. You can pass any kind of object with a symbol value pairs, and these will be used as keyword arguments for figure and axis respectively. To plot two things into the same axis, you can use the mutating plotting functions like lines exclamation mark and a scatter exclamation mark. Here I have plotted two lines on top of each other. You can also set plotting function attributes via keyword arguments. For instance, here I have specified the color and marker size. You can also manipulate most plot attributes afterwards with the syntax plot.attribute equal to new value. A lot of attributes can be set to either a single value or an array with as many elements as there are data points. As an example, it's usually much more performant to draw many points with one scatter object than to create many scatter objects with 1 point each. Here we vary marker size and color. You can also use an array of colors directly, in which case the color range is ignored. If you add label attributes to your plots, you can call the axis legend function to add a legend with all labeled plots to the current axis, or optionally to one you pass as the first argument. We can make subplots by giving the location of the subplot in our layout grid as the first argument to our plotting function. The basic syntax for specifying the location in a figure is fig rows as the first argument and columns as the second argument, as we have already discussed it. We can also create a couple of axes manually at first and then plot into them later. For example, we can create a figure with 3 axes and then we continue to plot into these empty axes. You can also create a legend manually and then place it freely wherever you want it in the figure. One way to create legends is to pass one vector of plot objects and one vector of label strings. The color bar works in a very similar way. We just need to pass a position in the figure to it and one plot object. For example, in the heat map example that we see, we split the return value of the heat map into 3 parts: the newly created figure, the axis, and the heat map plot object. This is useful as we can then continue with the figure FIG and the heat map HM, which we need for the color bar. The previous short syntax is basically equivalent to this longer manual version. You can switch between those workflows however you please. Guys, do not forget to like this video and subscribe to my channel for more Julia programming tutorials. Also check out my video on how to plot in Julia, in which I discuss the Pluto.jl package for visualization in Julia programming language. As always, see you all later.